Hello everyone, this is Jason Kendall again with another introductory astronomy lecture. Last time we were talking about distances between the Earth and the Sun, and the Earth and the Moon, and the Sun and the Earth, and trying to determine how far away they are and so forth. And we ended up looking at trying to determine the size of the Earth, but yet we really didn't have a good definition for the size of the Earth's orbit around the Sun. And we didn't even get to the point where we described exactly how we know the Earth goes around the Sun. Because for almost 2,000 years, the geocentric model, this geocentric apparent or settled science of the world was geocentrism, meaning it thought that Ptolemy's model of the cosmos, with the Earth at the putative center, with all the planets orbiting around it on deference, and on deference we're on had epicycles, and the epicycles were centered on difference, and the difference weren't actually at the center on the Earth, but were centered somewhere halfway between the Earth and something called an equant, and then that was not really the same, and every planet had its own equant, its own different, and set of epicycles. Yeah. It's pretty complicated. So the geocentric model of the cosmos is an extremely complicated thing. So what happened then in the latter part of the 16th century? The 16th century saw what we call the Renaissance across Europe. The Renaissance started to actually try to bridge gaps between things. New ideas were flourishing. There was new trade across Europe. And most importantly for us, it was the beginnings of the stepping stones of getting us to what we would call the science of today. So the mid-15th, but it starts in a very strange place. In heliocentrism, the notion that the sun is at the center of the solar system, not just the cosmos, if you will, is actually it starts the scales start to drop, but they don't really drop until something is really heavily done. So let's actually look at what happened. So Ptolemy's structure of the cosmos persisted well into the 1500s, roughly the 1530s or so. And then came along Nicolas Copernicus. And Nicolas Copernicus said to himself, as a mathematician, as a Renaissance man, as a person who wished to actually play around with mathematics and contribute, he wasn't a scientist, he was more of a mathematician, but his science actually was he didn't, well, no, I shouldn't say he wasn't a scientist, I should say specifically he was not an astronomical observer. He utilized the data that was embedded in the Almagest in order to make a new model of the solar system and the cosmos. And his model was kind of a geo-heliocentric kludge. Now, typically when you talk about this particular time, you say, oh, the Copernican revolution, this is the time. Copernicus comes along and says, sun at the center, and here we go. This is now the time for revolutions. Well, this is the thing about it, is that when Nicolas Copernicus came around, he was looking at it mathematically, and he saw Ptolemy's model, and he saw that there was a deference, and he saw there were epicycles on deference, and then he saw these equants. And the equants, there was these three pieces to the models, and everything was perfect circles. So you had perfect circle deferent, a perfect circle epicycle, and then everything was off-centered from the Earth by the in the direction of the equant halfway between. So this equant really bothered Copernicus. So he said, I'm going to redo all the mathematics such that the sun is at the center. I can eliminate the equants from my mathematics and see what I get. Well, what he got was the sun at the center of the entire cosmos, but kind of. So the sun at the center meant the following, is that every planet orbited the sun, but as they orbited the sun, they had to, but the centers of their orbit weren't the center of the sun. They were the center of the Earth's orbit around the sun. You see how that works? That's kind of weird. Let's do that again. So it wasn't the center of the sun. They weren't centered on the sun. All the planets' orbits outside of, like specifically Mars, Jupiter, Saturn, those were specifically centered on the sun. They were all centered on the Earth's center orbit, with the sun offset from that center. So it's a little confusing sounding, but wait a second, did he make it perfect? Well, here's the thing. There still were the deferents. The deferents were basically around the center of the Earth's orbit around the sun. And then but every planet still wandered on epicycles on top of these deferents. In fact, if you look at the mathematics, they were much more complicated than Ptolemy's. So a lot of people, when Copernicus published his data, it was like, wow, this is a great idea, it doesn't do anything for us. It doesn't actually help. In fact, it doesn't simplify. There was no great simplification from the idea of the geocentric orbit to the sun-centered orbit. However, one of the driving reasons for Copernicus's action was that he was a humanist, and humanists felt differently than the medieval Christian thought of the surrounding era. And it was the sense that as humanity was learning more and more things and becoming greater and greater masters of the environment and greater masters of what they could possibly do, that they were becoming more like God. And since he was a minister as well, he was a clergyman, Copernicus was, and he was welled up with the wonder of that was happening all throughout the Renaissance. What the fascinating thing is that medieval Christian thought adopted Aristotle's idea of a geocentric universe and embedded it into Scripture. But here's the fascinating thing about that is that the philosophy grew around it to give the earth, to people on earth, a great sense of humility. So the center of the earth was the farthest place you could possibly be from heaven. Heaven being the celestial sphere where all the stars are, that was God's realm, that was heaven's realm. And so being at the center of the cosmos was as far away from the center as you could possibly be. And if we look at Dante's Inferno, we find that if you wish to go to hell, you go underground, deeper into the earth. And everybody knew the earth was round, so you get closer and closer and closer to the center of the earth, and that's where the devil is. And so we think even in Greek mythology, the river Styx goes into the earth, and Orpheus descends into the earth in order to get his Eurydice. So one of the ideas of the humanists was to say, no, we're not the worst place in the cosmos, we're better than that. So we're going to elevate the earth. And so Copernicus had the idea that he was going to elevate the earth out of its humble position at the center of the cosmos. Not its elevated position, but its humble position as the maximum distance possible from heaven. And place it closer towards the heaven by having it orbit the sun. So if the earth was orbiting the sun, it was closer to heaven, which gave greater prominence to humanity. And that was an essence of humanist thinking. It was a philosophical change in thought. And so a lot of people rebelled against it for that reason, that philosophical reason. Well, here's an important thing that occurred. His model, his mathematical model, wasn't really any better than Ptolemy's. And there was still the problem of the winds, of all the parallax that wasn't seen, all these things that Aristotle said that were arguments against the motion of the earth. Now Copernicus just simply said, hey, the mathematics works, I've gotten rid of the equants, but it's just as complicated as Ptolemy's, and it doesn't explain away Aristotle's arguments. This is a problem. So people weren't really thrilled with Copernicus's model, and people had problems with it when they advocated it. There's some significant social problems if you advocated his idea, because it went against church doctrine, which followed Aristotle. In any event, so what it took was actual development of technology. But shortly after the 1540s, in 1572, there was a nobleman in Denmark by the name of Tycho Brahe, who looked up in the sky and saw a great star appear in the constellation of Cassiopeia. And that star was a supernova. And in 1572, that star made Tycho Brahe famous all across Europe. In 1574, he wrote about it. He wrote extensively about it. And it was his books and his writings about the supernova of 1572 were read all over Europe. And he became a superstar. He was kind of like the Einstein of the day because everybody knew him. Everybody knew about Tycho's star. Even when it was happening in 1572, they thought of it as Tycho's star. So in 1574, he became world famous. And in 1576, as a result of him being world famous, he went on tour doing scientific things for his king. And in 1576, his king said, I want you to be a lord. I want you to be closer to court. I want to keep an eye on you because you're really famous. But because of your great accomplishments, I'm going to make you a lord. So he made him Lord of Ven, which was a little island off of Denmark. Now, Brahe wasn't really interested in doing that. He wanted to do science rather than be like a courtly person. So he said, look, here's what I want to do. I want to build an observatory on Ven. And the king said, well, of course, why don't you go to it? It'll be a great thing. In fact, make it the best. And in fact, that's what Tycho Brahe did. He wanted to make it a research institution for astronomy, which is exactly what he did. He built the first custom-built observatory in 1580. And it was called Uraniborg, inside a castle on that little island of Ven. So in 1577, during the course of the construction of the observatory, a great comet was seen in the sky, and that was attributed to Tycho Brahe. And Tycho Brahe was now regarded as one of the great observers of the great astronomers of his day. In fact, his fame was so wide that his two kinsmen, Rosencrantz and Guildenstern, from Denmark, were featured highly in a play by a certain English playwright named Shakespeare in the play Hamlet. Go look it up. By yond new northern star, Horatio. And the play is actually properly titled A Disaster, or Bad Star, the Bad Star of Hamlet. And so there's some mirroring between the story of Tycho Brahe and his inevitable fall in 1600 that actually Shakespeare wrote about. In any event, so in 1580, he built Uraniborg, which was a dedicated observatory that was based on his fame. And so what he did for the next 20 years was do incredibly detailed observations of Mars. Why did he do this? Well, he discovered that since the Almagest was written in 140 AD, and monks were copying it and copying it and copying it, that transcriptions of these copies were getting errors. And so somebody had to finally go and actually update the thing by actually making new observations. So Tycho Brahe said, I'm going to do it. I'm going to be the guy. So he went out and did it. He made extraordinarily accurate observations, timings of the positions of Mars in the sky. And so he became an incredibly important person by his observations. He published his data, but by the end of the 1590s, he fell out of favor with his king and was exiled to Prague, and he had to get the heck out of there. So he was gone for various reasons, and he died in 1601. And when he died, his observatory was destroyed upon his death. But it wasn't too late. When in 1600 in Prague, he was met with by a young mystic named Johannes Kepler. And Johannes Kepler joined Tycho in Prague and worked with him and tried to wrestle the data that he'd gotten, that Tycho Brahe had taken before he died. And Johannes Kepler used that data. He worked very hard to get the data away from Brahe and away from Tycho Brahe's wife, who was his widow, and because Kepler was not a nobleman. So she didn't think that somebody who was not a nobleman should have that data. In any event, he eventually got the data. He eventually wrestled away because the local royalty saw fit to give it to him. And what happened was he looked at the data and analyzed it and tried all sorts of shapes with the data in order to see it. Can you make the orbits of the planets with circles? Do you need the epicycles? Do you need the difference? Where can you put these things? He rejected Tycho Brahe's version of a geo-heliocentric model, where Tycho Brahe even made his own model out of his own data, and Kepler just said, nah, that can't work. And what happened is that Kepler tried all sorts of methods, and finally he gave up on the perfect circle. This perfection, this concept of perfection, that was a thread from Aristotelian philosophy, that all celestial motion goes in perfect circles, that it always is perfect and it never changes and it's unchanging. This concept of perfection lasted for almost 2,000 years, and it was an infection in the mind, a meme, something that people couldn't get rid of, until Johannes Kepler just got so frustrated and demanded to know exactly how the shapes were that he tried an ellipse. Instead of using circles, he tried an ellipse. So he said, wait, if I make the orbits not circular, but ellipses, guess what? And put the sun at the focus of one ellipse, then it works. I don't need equants. There is already a built-in equant. It's called the other focus of the ellipse. I don't need epicycles because the shape of the orbit is already taken into account. So Kepler determined in one fell swoop two laws, in which he published in 1609. He published his first law of planetary motion, that all planets orbit in ellipses. And ellipses have a particular shape. They're not circles, they're more like ovals. So they have a particular shape. When they're nearest the sun, we call that perihelion. When they're farthest the sun, they call that aphelion. And the average distance between the sun and the planet along the ellipse, we call that the semi-major axis. So the semi-major axis is simply the average distance between the sun and the planet on there. Second of Kepler's laws that he published in 1609 was the area that as a planet orbits the sun, the line between the planet and the sun sweeps out an area. And so if we determine what the area is that is swept out by that line, say in a week's time or a month's time, but it'll always sweep out an equal area in an equal time. Which means that when it's closer to the sun, it's moving faster, so it's sweeping along that orbit, so the triangle is wide and fat. But when it's far from the sun, it's actually a narrow and thin triangle. That's at aphelion, it's a narrow, long, thin triangle. But at perihelion, it is a fat, wide triangle. And so the appearance of the triangles might be different, but they have the same area. And so they sweep out equal areas in an equal time, which means that as it's at perihelion, it's going faster, and when it's at aphelion, it's going slower. Funny thing is, in 1609, after publishing this, Johannes Kepler learned about a young man named Galileo Galilei, and he sent a copy of his Astronomia Nova to him, and Galileo completely ignored it. Wonder what would have happened if he didn't. Anyway, so in 1619, Kepler further looked at the data and studied it extensively. He wasn't completely satisfied with the appearance of it. And he said, well, wait a second. If I look closely at this, I notice that how long does it take that things go slower the farther away from the sun they are. And he found that the time it takes for a planet to go around the sun is a very simple relationship to the average distance it has from the sun. So the period of the orbit, in terms of Earth years, squared, is the same as the average of the distance between the planet and the sun, cubed, if that average distance is relative to Earth distances from the Earth to the sun. So now we've got this thing which is really fascinating. It's called the harmonic law, and it's sometimes just written p squared equals a cubed, where p is the period of the orbit around, and a is the semi-major axis of the orbit of the planet around the sun. So once again, the square of the time it takes the planet to go around the sun in units of Earth years is equal to the cube of the distance to the planet from the sun in Earth-Sun distances. And those Earth-Sun distances are called astronomical units. So the p squared equals AU, p squared equals a cubed, where p is in Earth years and a is in AUs. So of course that's 1 equals 1 for the Earth. And for Venus, it's the period is the A is about 0.72, and so I forget what that works out to be for the average distance is 0.72. So the average year is a few hundred days, is over 200 days. And for Mercury, it's about a third of an astronomical unit, and so it's about 88 days for its orbit around the sun. So what's fascinating is that this provides a relationship between all the distances. So if you can get, using Kepler's laws, because this is a law based on observations that Kepler did, well, not Kepler, that Tycho Brahe did, based on all the planets. So Tycho Brahe did accurate observations of all the planets. Kepler fit them with ellipses, found that the ellipses had specific semi-major axes, and found in 1619, published in 1619, his observation that the time it takes for a planet to go around the sun has a direct relationship to how far it is from the sun. So, and they're all referenced with respect to the distance between the Earth and the sun. So if we can just get that distance from AUs, so if we could just learn that, then we can get everything. Well, fascinatingly enough, the next guy to come along, we're going to talk a bit, next time we'll talk a bit more about the people who missed out on this. Galileo missed out on Kepler's work, but we can't really fault Galileo for that, because in 1609, when he sent it. Actually, Kepler in his later years went back and looked at his work, Astronomy Nova, and found that even he couldn't read it. So you can't really blame Galileo for not reading something that's basically impossible to read because of its complexity. But Kepler's laws were actually the beginning of what we call astrophysics, because he took actual observations and then created a theory surrounding them and did some sort of explanation on top of them. Now, this is really some fascinating stuff. And if we look at it, we say, well, wait a second, this is the beginnings of things. And so we're going to skip over to Italy in our next talk. And then after that, we'll skip across the waves over to England, over to England to see what Newton is going to do with it. But Kepler was on the verge of was one of the great stepping stones in astronomy. And if we look closely at what he did, when he passed, we actually look at some of his writings as he gets later in his life. We find that one of his most important works comes at the end. He was still a mystic to his very dying days. He really wanted to understand the mind of God. That was his goal with understanding these orbits. So when he wanted to understand that, he actually chose to say, well, what does this mean? And all his studies from the stars, when he looked up at them, his last writing was called The Dream, and the Somnium, the Dream, where he actually looked up in the sky and said, I dreamed a dream that the stars were each of them surrounded by planets, just like our sun is surrounded by planets. And if it is surrounded by planets, then there are other places where other beings are looking down or up at us at a night sky. And each of those stars could have thousands of people or millions of people looking at us. And uncountable stars could be seen with the telescope that would have been invented during the latter part of his life. So really, Kepler kept his dream alive. And he thought in his last writing, which would be heretical even for that time to even talk about, was he dreamed of life on other planets around other stars. Okay, so next time we'll talk more about the revolution that began science. Hello, this is Jason Kendall, and welcome to my next of my introductory astronomy lectures. Last time we were talking about Kepler's laws and how Kepler discovered that the Earth goes around the Sun in an ellipse as well as all the other planets. Now, Kepler discovered this and published this first in 1609 for his first of his two laws, and in 1619 published the third of his laws, the p squared equals a cubed law, or the harmonic law. So basically, a very, very, very deep opinion, so it's propagating about through Europe, that the Earth, the planets move about the Sun according to Kepler's laws. Well, what we didn't talk about is a particular person that is typically credited with actually having done the whole thing. And he was an incredible figure in all of science and is considered to be the father of science. His name is Galileo Galilei, and he was a scientist, mathematician, public figure from who was born in 1564 and passed away in 1642. Well, Galileo Galilei, which is basically his first name twice, like me named John, right? So the Galileo Galilei, he actually did an enormous amount of work to try to propagate the idea of the Copernican model of the solar system, meaning specifically the Copernican model, the sun at the center, with all the planets going around on circles on circles around the sun. Now, this was Brahe's, not Brahe's idea. Tycho Brahe had the idea that the sun went around the Earth and Mercury and Venus stayed with the sun and orbited that. That was the Tychonian system. But Kepler used Tycho's data in 1609 to deduce the ellipticity of the orbits. But Galileo received this information in 1609, received it from Kepler, and ignored it. Well, because as we learned before, that Kepler's writing was very opaque, and even Kepler himself later in life couldn't actually read it. So it was pretty opaque work. However, we credit Kepler with having discovered the laws, but this happened simultaneously. So let's see what Galileo's story is, because very often people associate Galileo with being excommunicated by the church, and there's an enormous church science battle. And in fact, some of them were the mythology, I'm just going to call it mythology, where the story of science against the church arises. So let's actually see a little bit about what happened, what Galileo said, and where we're going with it. All right, so Galileo espoused the Copernican model because in the 1590s, he considered the nature of the tides, and more specifically, he considered what it meant that if you were in the bottom of a ship, if you were in a ship and the ship was sailing across the sea, and the ship was sailing, let's say, 20 knots under a nice stiff wind, and there were no waves, it was a glassy sea, and you were in the hold, you would not be able to tell, he asserted, that the ship was moving. So since you could not tell that the ship was moving, how would you not tell? Well, okay, if the ship were moving, one of Aristotle's arguments is, if you're in the hold of the ship and you take a ball and you drop it and the ship is moving, then the ship should move out from under the ball and the ball should fall behind you. And you should see an arc inside of the ship. Well, we don't see that. What we actually see is that the ball falls straight down. So inside the ship, as the ship is moving, and with no reference to the outside, no way to see the outside, if you take a ball and drop it straight down, it goes straight down inside the ship. It does not fall behind. Things don't accumulate at the back of the boat as they fall or rise or drop. So this was Galileo's idea, and he said, well, wait a second. If the ship is moving, you can't tell it's moving. So if the Earth is moving, then we can think of it as a ship through space. And so therefore, everything would be carried along with it. Now, how does it get carried along with it? Galileo couldn't answer that question, but he posited it from a structure of relativity. And that idea was the one that made him convinced that Copernican model was true. All right. So Galileo was also a man of deep faith, and he was a courtier in the Venetian Senate. He was friends all across Rome and across all of Italy, and he was a very important man. So, but he also was an incredible troll, and he did a lot of things. A troll meaning like internet troll, meaning he really made a lot of people angry with the way he talked, the way he argued, and a lot of things. And part of the reason for his later trial in his life is because he made a lot of people angry, even his friends, for no good reason. So we'll see how that works later. Okay, so basically, when Galileo was convinced that the Copernican model, specifically Copernican, not Kepler's model, but the Copernican model was true, he wanted to make sure that the church followed this idea because as a man of faith, he wanted his church to be at the vanguard of understanding. He did not want it to be pushed back in time and looked at as something that was behind the times. He wanted his beloved church to have access to the greatest of all knowledge. And so there's a certain sense of humility there. But really he was trying to go after that. So in 1609, he heard about this device being created called a far-seeing look glass. And a far-seeing look glass is basically a telescope. And that's the name that was given to it later. But it was developed in Holland, and Galileo said, wow, he had no idea what they were. But since he knew how to grind lenses, and he was the best one in the area, in Venice, to do that, he basically ground a whole bunch of lenses and created his own telescope. And when he did so, he said, wow, look at this amazing telescope. He went to the Venetian Senate, showed it to them, and sold them, and said, this will help you with, he sold it for an exorbitant amount of price, and he also asked for a huge amount of money to actually get it, to use for his goods. And basically, he convinced the Venetian Senate that it was useful for military purposes because you can see ships in the distance, and that it was his, and he should be the one to get money for its discovery. Well, they were convinced, they gave him the money, they gave him position, and then a few days later, a whole boatload of telescopes came in from Holland, and his money was taken away and his position was taken away. Well, this was kind of annoying to him, so he wasn't daunted. He still had the telescope, and he still had thought about the geomobility argument, meaning the Earth moving through space, and he said, okay, fine. Now, I know that Ptolemy could be wrong if I can observe things. So he started looking at the sky, and he utilized his telescope in 1609 to observe things. And the first thing that he did was he looked at the moon. And when he looked at the moon, he saw the moon had valleys and craters and mountains, and it wasn't perfect. Now, perfection is an important element, because remember, in Copernican thinking and Aristotelian thinking is that the heavens and all things of the heavens were perfect by their very nature. If you're in the heavens, you are by definition perfect, and therefore the moon has imperfections. This is a problem. So it's a philosophical argument. The next thing he noticed was that the sun also had imperfections. These are sunspots. He said, well, wait a second, it's not a perfect orb. It has these dark surfaces on it, and that means it also is imperfect. Well, there's another interesting argument. And third, he went further and discovered that when he pointed his telescope at the sky, around the Milky Way itself had many more stars visible than can be seen with the naked eye. And so one of the core essences of Scripture was that the purpose of the stars at night was to illuminate us in our day at night. So how do stars illuminate us if we cannot see them and they can only be seen with a telescope? Now the next one that really got it going was in January 7th of 1610. He pointed his telescope at Jupiter and started making observations of Jupiter. And he found that Jupiter had a series of moons. Well, not moons, other stars. Remember, to everyone, all the planets were stars. They were wandering stars. That's what planetas means. It means wandering star. So he saw that 3 stars wandered right next to Jupiter. They did not have anything that looked like that was fixed with respect to them. There weren't any strings attached. But these 3 stars stayed in a line and went back and forth around Jupiter as Jupiter moved through the sky. And if Jupiter can have satellite stars, then maybe the moon can move with the Earth. Because that was one of the great arguments also against the movement of the Earth, is if the Earth moved, well, then it would leave the moon behind. And since we knew the moon orbited the Earth, that's been known since antiquity. So if the Earth moved, it would leave the moon behind. And therefore the Earth cannot move because it would leave the moon behind. But Galileo just observed that there are 4 little dots, 4 satellite stars that orbited Jupiter and were not being left behind. So maybe the same can be true maybe the same can also be true of of Jupiter, of the Earth and the moon. All right, so this was nearly the clincher for him. But the one that was most important for him was the discovery of the phases of Venus. Now, the phases of Venus were the clincher. In the Copernican model, the phases of Venus can have a full set of phases because Venus can be on the far side of the sun with respect to the Earth, and if it's that way, then you get a full phase for the moon, basically a full phase, just like you get a full phase for the moon. You can get a full phase for Venus, but Venus would be very far, so it would be very small. And when it was close to the Earth and very, very bright, it would be in a crescent phase and very large in a telescope. So Venus would have all the phases of the moon if the Copernican model was correct. If the Ptolemaic model, the geocentric model, was correct, where Venus spends its time on an equant between the Earth and the sun, then only new phases and crescent phases and maybe quarter phases could possibly be done by Venus. Now, Galileo observed Venus and discovered full phases. He looked he watched it during 1610 and learned that there were a full set of phases that Venus had. All right. This was an enormous, enormous, enormous undertaking. When he discovered these phases, that fully convinced him that the Ptolemaic model was by definition wrong. So he went off, and he was so proud of himself that he took these 5 observations of the moon's imperfections, the sun's imperfections, Jupiter's satellite stars, the Milky Way's excessive stars that cannot be seen, and phases of Venus, and put them together in a little book called The Starry Messenger. Now, The Starry Messenger he dedicated to the family of the Medicean family, and he named the 4 stars of Jupiter after the sons of the Duke Medici. And so that was to flatter him and get money, and it worked. And he became a sensation all over with the Starry Messenger. And this was his first major argument in favor of Copernicanism. Specifically Copernicanism. Remember, he wrote this book in 1610, which is 1 year after Kepler did his work and published his two laws, and Kepler had delivered his laws to it, and people were starting to think Kepler was pretty much on the right track. But Galileo was saying, we got to look at this thing. We have to look at Copernicanism, and Copernicus was right. So on 1610, he published The Starry Messenger, became a sensation, and everybody looked at him. Now, one of the things that Galileo did that became a problem for him was because he was such a man of faith. He used arguments of Scripture to support him, rather than doing a pure scientific idea. And pure science would say, well, here's what we think is the best explanation for the problem, for the observations, and here are the problems with our observations, and here's what we need to solve. What he said is, this is true. And all of his friends in the papacy, in the Vatican, said, you can't really say that, because if you're going to use Scripture, Scripture is by definition true. So if you're going to use Scripture to support science, Scripture itself says what is true. And Galileo said, but wait a second, wait. There are all sorts of arguments that, and then Scripture said, okay, so Galileo tried to go against Scripture. And it's important to note at this point exactly where in the Bible these things are. And one of the locations is in 1 Chronicles, I think it's 16:30, and there are a number of Psalms, 93:1, I'm reading them off here, 96:10, and 104:5, as well as Ecclesiastes 1:5. But Galileo also used the writings in the book of Job, 9:6 and 26:7, to actually demonstrate that possibly the earth could move. So Galileo was battling Scripture with Scripture. Now, he's a mathematician and a scientist and a lecturer. That's not his job, especially in medieval Europe or Renaissance Europe. The job of interpreting Scripture is for the papacy, is for the Ecclesiastes. It's for the ecclesiastical, not for science. So this was a problem because Galileo was taking, as a lay person, he was taking on the jobs of a priest. Now, that was heretical. So in 1616, his writings were deemed heretical partly because of that, partly because of his upstart nature, and he was utilizing Scripture to boost his position. Now, that can be a really big problem. So basically, he should have used science as his argument. Fundamentally, though, his main observations were with this telescope and the phases of Venus. So that was what he did. And the rest was trying to utilize people's words against them. So it went on for a while. His writings were to some extent banned. He did some other things later on, and basically he wasn't as in the hole as most people think. He had good friends all throughout the papacy and people who defend him and talk to him, and he was a friend of the Pope. He was a friend of the entire thing. But here's what happened that was critical, that really kind of set the stage for Galileo's rise, for his incredible rise, and his meteoric fall. So in 1623, his good friend, Cardinal Maffeo Barberini, what he did is he was elected Pope. Now, Barberini was a friend and supporter of Galileo's. And what he said was, okay, you can, he gave him permission, or at least seemed to give Galileo permission, to write about the nature of the two world orders. This is 1623. This is 4 years after Kepler had delivered his harmonic law, and it was actually quietly making its way around to say, hey, this seems to be a really good way of actually plotting it, use ellipses. And Copernicanism, by 1623, had been almost thoroughly debunked. I mean, specifically utilizing Copernicus's model of perfect circles with ellipses on ellipses and so forth, in favor of Kepler's model. So people across Europe were quietly using Kepler's model while Galileo was loudly proclaiming Copernicanism. All right. So in 1623, Barberini was elected Pope. Then Galileo said, my gosh, this is my opportunity. I'm going to write this whole thing out. So he wrote a book. And the book was called The Dialogue Concerning Two World Orders. And it took him until 1632 to publish it. So what he chose to talk about was he tried to actually discuss the dialogue concerning two world orders. What he chose to talk about in this book was to say how the Copernican model met up against the Aristotelian model. Now, in 1632, when it was finally published, Kepler's laws had been out for more than a decade, and yet he makes no mention in this book about elliptical possibilities and geomobility across ellipses. Galileo was really wanted to actually prove this using rhetorical arguments. So in 1632, when he wrote the thing, or actually published it, one of the main arguments is, as I said, was that the curvature of it, as you ride along with a vessel, if you drop something in the vessel, it does not fall behind you, so therefore things can move. And so he had three characters. And three characters in the book were Salviati, which espoused Copernicanism and espoused the ideas that Galileo thought were appropriate. And then you had Salgredo, and Salgredo was a neutral party trying to decide between Earth-centered cosmos, a geocentric universe, and a heliocentric universe. And then, to represent the geostationary location and the Aristotelian viewpoint of antiquity that had been around for more than 1,400 years, was a character named Simplicio. And Simplicio was an idiot who did not understand any of the arguments. He was written as a dunderhead and a thickhead. So Galileo wrote this as a dialogue between these three people over dinner, over lunch, and it's a magnificent book. It's extraordinarily funny. And when it was being written, and as it was written, it was received quite well, except for the people who held Aristotelian views, because Simplicio was regarded as a complete fool. And basically Galileo attacked a huge number of his scientific colleagues and said, you're basically a bunch of simpletons, you're a bunch of idiots. Now, one of the most important elements that Galileo learned that he had to understand in writing this book was that he was instructed, okay, if you're going to write this, you need to make sure that you give both sides equal time, that the geocentric word gets the last view, and that everything is presented in terms of scientific ideas, meaning you have to show that both ideas, where their flaws and their benefits are. Because the church wasn't interested at the time in really destroying Copernicanism, it was trying to show that if it was going to suppress Copernicanism, it needed to show that it totally understood every aspect of it. So you can't suppress. So this is an interesting viewpoint. So they wanted to demonstrate that they actually understood the Copernican viewpoint. And they were going to utilize Galileo's writing to help demonstrate that. And that's part of the reason why he got the license to write the book and to publish it. But Galileo did everything wrong. He made everybody angry. He pissed off everybody. It gave Copernicanism the last word. He made the Simplicio look like a fool. Angered everybody. So in the August of 1632, Galileo was brought on trial for heresy in front of the Inquisition, and there are many of the reasons why. If you look at the actual reasons, none of them were saying like high crimes against this, but mostly it was like, well, you just there were all sorts of minor things, and in fact the Inquisition itself said many of these things could be corrected, except for the disobeying part. And part of the disobeying part was that Galileo used Scripture to try to bolster his ideas. And Scripture is truth, by definition, because that's what Scripture is for everyone. But science by itself does not describe truths. It describes the best possible explanation for physical phenomena in the real world. So these are the best explanations for the evidence that we have gathered. And Galileo used Scripture instead of science. And that got him in a huge amount of trouble because now he, as a layperson, was up against his beloved church. That was a problem. So Galileo had to recant his, as he went through the trial, it actually spiraled out of control from him. And it could have been fixed. But he chose to resist as he could because he was an arrogant man who was in the habit of insulting people. But it ended up that he had to recant. I don't believe that the story of whether he was shown the instruments and then he recanted. That is most likely apocryphal. But what happened with Galileo was he was instructed not to write about this, not to hold Copernicanism for the rest of his life, and so on. So he lived another 12 years. He died in 1642, but he was under house arrest, and he could not publish data on the world orders for the rest of his life. Now, he was a very smart man, and he actually then decided to write down his arguments on motion. So he started to develop ideas and writings about how things move, how things go down inclined planes, how things fall, how things accelerate. And it's amazing what he did when he finally was forced to just sit in one place and think, rather than go everywhere and tell people what to think and telling people what to do. Once he was under house arrest, he actually wrote one of his great books on motions and on how things move. And that book was later used by Newton in order to understand and develop the calculus. So had he not been put under house arrest, Newton would have had to develop even more things. So, well, and there's also an important side note, is that Galileo's daughter, whose story is written about by David Sobel in an amazing book called Galileo's Daughter, Celeste, his daughter, was an incredibly intelligent woman in her own right, and she actually helped edit Galileo's final book. So she lived in Abyss, very close to where her father was being held in house arrest, and it was a very poor abbey, and so she actually helped him write what he was doing, because as time went on, his eyesight was failing. He had extraordinary rheumatism, which he had had even since the 1610s, and so it made it very difficult for him to get around. So he had all sorts of health problems, and so she helped him write this book. So we have Galileo's daughter to thank for her dedication too, and she's an unsung hero of physics and astronomy, and in fact all of science, because she probably helped him through it. And the letters that are extant from between the two of them show that they kept in contact for a very, very long period of time and discussed matters of many, many matters, and both of the faith and of science. So Galileo is credited as being the father of science because he was such an outspoken proponent for ideas that were based on evidence. So he took a telescope and he looked at things rather than using handed down ideas from Aristotle. Now, he tried to then back his data up by using scripture and using people's arguments against him, but really he actually took the observations himself, interpreted them himself, and then published them himself. That was the main essence of it. So he was an integrated experimentalist and observationalist experimentalist and theoretician at once. Now, Kepler took somebody else's data and created an extensive set of theory around it, a mathematical theory, and that's being an astrophysicist. But Galileo, because he was so incredibly loud, brought so much attention to it that even though Copernicanism, with the specific idea of the Copernican model of the cosmos, had been almost thoroughly discredited by 1632, and everyone was quietly using Kepler's laws because they actually worked, nobody actually espoused Copernicanism, and even Galileo didn't know about it, didn't actually acknowledge the existence of Kepler's laws in all his writings. But be that as it may, we consider Galileo the father of science because of the great sacrifice and great effort that he went to in order to make sure that these ideas were known widely. So he actually did fairly little actual observations of the heavens. His eyesight wasn't fantastic, but his contribution with his later writings, as well as Starry Messenger and the Dialogue, contributed greatly to the advancement of science and allowed for ideas such as Kepler's, the mathematical ideas, to be smoothed. Because his ideas were quietly rising, but Galileo made a big explosion on the map. And those big explosions everywhere helped shake things up such that ideas based more on observation and logic could flourish. So there we go, as the next thing, and so next time we'll see exactly how Galileo's ideas then propagated forward into the future. Hi, this is Jason Kendall, and welcome to the next of my introductory astronomy lectures. Well, last time we did an extended dance remix version of Galileo's struggle to bring the ideas into fruition for modern science. And what we learned was that at the end of this whole thing, he had ended up in trial under house arrest and so forth. But I want to do a short discussion on the details of all that and get into the details and see what we can get. So at the end of this, we're going to see where Newton's ideas rise out of. All right, so Galileo, having found that the Ptolemaic system is completely dead because of the phases of Venus. The phases of Venus to him were the key element of everything. The phases of Venus cannot be what they are in the sky through observation without there actually being, without the Copernican system or something where the sun is at the center. So Galileo advocated Copernicanism, even though pretty much nobody was doing it by that time. But the Ptolemaic system was completely dead because it incorrectly predicted the phases of Venus that are observed. All right, so what happened later is that when Galileo finally published his dialogue concerning two world orders, got himself into a bunch of trouble with the Inquisition and was placed under house arrest for the rest of his life, what he then did with his daughter Celeste, who was a nun and keeping herself away from, possibly dying in childbirth, but being a very intelligent young woman all of her own, she and her father wrote the dialogue concerning the two new sciences. And so this was Galileo's, one of his great masterworks, which he published in 1637. And this is interesting. He was under house arrest. He was told not to publish anything at all under pain of death. That's what house arrest is. And if you're an academic whose word was going against the church, this can get you in some serious trouble. In any event, he published this work, and the two sciences he were talking about, one was in the strength of materials, and the other was in the physics of motion. How things move, how things accelerate, rotation, things going down inclined planes, and so forth. And he did this while he was under house arrest, and it was published in the Netherlands. Now this is interesting, but the funny thing is that nobody really did anything about it. So he was under house arrest, everybody knew he published it, but he was not punished for doing so. And that may also be part of the perestroika version of the Renaissance, because they just wanted him to be quiet and not be such a troublemaker. And so it's like, okay, here's your really stiff punishment that we're saying we're doing, but in practical terms, let the guy be the guy. He was a very important person. So he was able to publish this amazing work, The Two Sciences of World Orders. And he again had the dialogue between Salgado, Salviati, and Simplicio, but this time Simplicio is not looked at as a complete buffoon. In fact, he's smart enough to carry his own with the other two. That probably helped to smooth over some of the relations that he had, and maybe that was some wisdom passed from his daughter to him about how to get along in the world. All right, so Galileo published this amazing, this final work of his, and then comes in 2 years later, Jeremiah Horrocks. He utilizes Kepler's laws, and he utilizes notes of Kepler's laws. Jeremiah Horrocks is in England, and he uses Kepler's laws and realizes that Kepler made a prediction for a transit of Venus across the face of the sun, or a near-miss transit on December 4th. Jeremiah Horrocks goes back and looks at the mathematics of Kepler and determines there will actually be a full-on transit of Venus on December 4th of 1639. At 3 o'clock in the afternoon local time. Well, Jeremiah Horrocks says, okay, I'm going to do this. I've made a prediction. The prediction based on Kepler's laws shows that there shall be a transit of Venus at that moment. Well, it's cloudy that day, but the clouds part at 3:15 p.m., and he's able to make a transit timing and therefore make an estimate of the astronomical unit, because the timing of the transits of Venus actually allows you to make an estimate of the astronomical unit, and therefore he gets a pretty good guess. He gets it wrong, but he gets a very, very good guess, and he's less wrong than pretty much everybody else prior to him. But most importantly, he used Kepler's laws in order to make a prediction about the transit of Venus, which was correct. And he had to make some corrections to Kepler's stuff. Everybody needs corrections, it doesn't really matter. And the thing is about Horrocks, though, is that for some bizarre reason, everybody in England publishes late. He never publishes his stuff until he dies in 1661. But Horrox is the first person to actually use Kepler's laws to actually make a prediction. And so it's becoming quite clear that Kepler's work is the way to go. But in 1641, though, let's go back over to Italy for a second. In 1641, because there's this great story that everybody hears about Galileo. At 1641, a friend of Galileo's, does some exercises. A Jesuit priest goes to Pisa, to the Leaning Tower of Pisa, and tries to demonstrate that when you take two balls and you of different weights, different compositions, different masses, and drop them off the Leaning Tower of Pisa, they hit the ground at the same time. All right. That wasn't done by Galileo. That was done by his friend Vincenzo Ranieri. And so Galileo was very pleased about this. But then Galileo passes away in 1642 and leaves all of his scientific data to his friend Vincenzo Ranieri to Ranieri in order to publish and work on. But Ranieri himself dies very soon thereafter. And it's their mutual friend Vincenzo Viviani who who attributes the Leaning Tower of Pisa and dropping things off of Pisa to Galileo. And thus a legend is born. So that's a wonderful thing to think about, that occurred. That's where it comes from. Galileo himself did not go to Pisa and did not drop things off of there. A friend of his did, and then another friend of theirs attributed it to Galileo, and a legend gets born. See, these things happen all the time, all throughout history. So Galileo has now passed away. 9 years later, in 1651, Riccioli republishes what he calls the New Almagest. Remember Ptolemy's Almagest, which was a tour de force of 400 BC, 480, of a very long time ago, a Greek astronomer, actually looking for the nature of how things work. But Riccioli says, all right, what he does is he argues and he goes through and looks at all the arguments in favor of the Copernican model of the cosmos and in favor of Tycho Brahe's model where the sun orbits the stationary Earth and everything orbits around that, because those seem to be the two dominant philosophical models. And he puts together, side by side, all of the arguments between Copernicanism and non-Copernicanism, specifically geostationary models and heliocentric and geomobile models. This was the book that Galileo was supposed to have written back in the 1630s. So finally it gets written, and it is an incredible influence because it's actually a scientific document, tries to actually weigh the arguments, and sometimes people say, well, there's more accounts against Copernicanism, so he weighs in favor of it. But it's not really the case. The most important thing to remember is that Copernicanism has a really tough thing that it goes up against. And there are two things. One is that if the Earth moves, where's the parallax of the stars? We still have not gotten to that. This is a big, big, big problem. So where's that parallax? And, well, you can't say that the Earth moves until you see parallax. And then second, we have the Coriolis effect, which would be, wait a second, if the Earth is rotating, then the poles would be rotating slower in terms of raw speed as opposed to the equator. So if Galileo's idea is to hold, when the idea of Galileo is that if you're inside the hold of a ship and you drop something, you can't tell if anything's moving. Then if you're at the equator, the dropped ball is moving along with the equator very fast. But if you're up near the North Pole, it's moving very slowly with respect to outside viewers. In both cases, inside of if you're up in space looking at the ball falling, if you're away from the Earth, looking down at the ball, you have a magic lens that allows you to see through the ship and see the ball being dropped. You'd see the ball scooting across like this. That's what you'd see up in space. But now if you see the same experiment done at the North Pole, where the Earth is rotating very slowly because the path that you go around near the North Pole is very short in 24 hours, so your actual speed is slower. So that would actually show a smaller speed. So therefore, if that's the case, what happens if your ship goes north? Then you should actually experience a change in speed or change in direction. And the Coriolis effect is that something that moves from the equator north will retain its motion of the equator as it goes north. So therefore, it should arc forward or arc eastward as it goes. And if it's coming from north going south towards the equator, it should arc westward or behind. And so that's the Coriolis effect. And we see that today in the pattern of storms like hurricanes and how they move and rotate. That's the Coriolis effect. It has nothing to do with things going down bathtub drains or toilets or so forth. It's all about enormous distances and differential rotation of the Earth. Coriolis effect does not apply to small areas inside of a bathroom. It just it's too small a difference in speed. If that actually worked, your head would spin because you've got a lot of liquid in your stomach. So if that volume would work, then you should feel Coriolis forces inside your stomach, and you don't. Any event. So the Coriolis effect is a prediction of a rotating Earth that is spherical in shape. And no one had observed it yet. So when Riccioli actually created this, he said, well, there's two main arguments against geomobility. And the first one is the lack of parallax, and the second one is the basic inability to find the Coriolis effect. These were, of course, later discovered, but this was a scientific tour de force to actually show the equal arguments, and this is what Galileo should have written 20 years prior. In any event, this was an important thing that still kind of favored geostationary, the Earth being stationary, not necessarily at the center, because everybody was going along with Kepler's laws. They said they work really well. So in 1655, Huygens built a new huge, Christian Huygens built an enormous telescope, looked at Saturn, and discovered the moon Titan. And by the 1660s, everybody had adopted Kepler's laws, and it was and basically the only thing they didn't use was the equal areas, equal time thing. They just thought that was silly. And in fact, they found that the tables of the Almagest, or the new Almagest, were easier to work with than the mathematics of Kepler, who was notoriously opaque. So they really, use what works, right? And if it works, works. But they really loved the Kepler third law, p squared a cubed. They loved that, and that worked really well. So ellipses combined with p squared a cubed. The second law they weren't so happy about, but yet it was clear that these things worked mathematically, and that makes for a valid theory. But does it make for real science, and does it truly answer the question if the Earth moves? All right, we'll leave that till next time. When we see how in 1687 everything changes with the publishing of Newton's Principia. Hello, this is Jason Kendall. Welcome to the next of my introductory astronomy lectures. Well, up until this point, we've been doing a lot of historical aspects and discussing how things arose out of the miasma of early pre-science. And we got through Kepler's struggles with Tycho Brahe, and we got through Galileo's trial and all of his difficulties and his findings. And yet we were left with something very, very, very important. What we're left with is that it's an unfinished business, because even at the end of Galileo's life, when he wrote about the motions and how things move, it still was not understood exactly how the cosmos worked above. So here's the thing that starts to happen. Everybody's talking about it all over Europe in the 1660s, assuming Kepler's laws are true, or at least work extremely well. And brilliant minds all across Europe are working feverishly to try to understand it. So it comes along in 1684 that Edmund Halley in London, Edmund Halley, Christopher Wren, and Robert Hooke are all sitting around talking, and they're in a conversation. And Hooke claims that he has derived an inverse square law that shows how the planets move, and actually shows how the planets move around the stars and derive the orbits of the planets. However, Halley presses him on it, and Hooke never actually reveals where he actually does it, or even reveals his writings. He just says, I've done it, but he never actually shows any of publication. Anyway, so because this is so pressing, and Hooke is just kind of this really strange fellow. Oh, by the way, a really good story for where you can actually where you can see this in a nice dramatic format is, I'm just going to cut away here for a second. Go see Neil deGrasse Tyson's Cosmos series that describes this particular effort. And it's a wonderful dramatization. So I'm going to kind of summarize pieces of it here. But basically, it's a pretty well-known topic. But let's continue on in 2-minute format as opposed to half-hour, 45-minute format. In any event, so Robert Hooke is basically a fellow that basically is domineering. He's just kind of a grumpy sort of old guy. And then there's this young man, Sir Isaac Newton, who is also over at Cambridge, and Halley goes and visits Newton over in 1684, knowing he's, after this conversation, probably around August or so, visits Newton and tells him about what Hooke told him. And Newton says, oh, I've already done it too, and I have it written down somewhere around here. I'm not sure where it is, and his papers are stacked. He's like a hoarder or an OCD kind of guy. He's also a mystic, and he's a very quiet fellow, so he doesn't feel like causing any controversy, because if Hooke says this thing, he doesn't want to get into a tussle with Hooke in any event. So Newton said he's already got it, he already finished it a long time ago. Halley's stunned. These two people have finished this thing, and neither one of them wants to talk about it. So it gets kind of crazy. But Halley persists and says, you really should do this. And Newton says, well, if Hooke hasn't done it, I guess I can do it, or maybe I'll show Hooke, or something like that. There was some deep competition between Newton and Hooke. And between about May of 1684 and the summer of 1686, Newton actually worked almost primarily on the Principia, which is his masterwork describing the motions of the planets and the motion and the work of gravitation. He invented the calculus in order to do it. Newton's secretary says basically there were no notes on anything about that Newton would talk about on any other subject of this during that time period. Newton was also known to be extremely eccentric in a lot of ways, and he would just go out on long walks and he'd forget to eat, he'd forget to bathe, forget to change his clothes. Sometimes he would go out walking, get a new idea, and run back in. Fairly standard obsessive. But Newton was a brilliant mind. And by 1686, the summer of 1686, Newton had written his books. And Halley then presented it to the London Society, to the Royal Society, and said, we need to actually publish this. And they'd already published, so they used up all their money for publications on a publication about fish, diagrams, illustrations of fishes. So they didn't have any money to publish this. But Halley thought it was so important that what he chose to do is he chose to use his own personal money to publish solo Newton's work. So the Royal Society gave him the go-ahead, and it was published in 1687, his Principia, Newton's Principia. And the Principia is considered to be one of the greatest masterworks of all of science. And in it, he describes his laws of motion and his law of gravitation. So what are Newton's laws that can be summarized out of the Principia? Well, they're the classics. The first law of motion says that any object that is at rest will stay at rest, or any object in uniform linear motion will stay in motion unless it is acted upon by a force. So it'll either keep going straight or stay at rest until it's acted upon by a force. Now notice this actually kind of holds with Galileo's idea of the things inside a boat. So basically the rock inside, or a ball inside the hold of a ship as a ship is going steady, is actually, there's no net force being applied to the ball inside it as it's dropped. So it keeps its motion, because it doesn't matter, according to Newton, whether the ball is dropping or being held by a person. It has a speed. The ball itself has a speed going this direction. When you release it, it then falls under the course of gravity, but it still retains that speed due to Newton's first law. So there's no new force acting upon it except for the downward force, which is gravity. So since there's no new force, it makes total sense why the ball falls straight inside of a held ship. And also it makes sense why if you set something on a table, it doesn't move, because there's no forces acting upon it. There's also, and something rolls straight across the table, if there's no additional forces, it keeps going straight. If it starts to turn, then maybe there's like a curvature, or maybe there's somebody attached like a string to it or something. But if there's no force to it, it'll keep going straight, or it'll stay at rest. In any of the next thing is like, well, then what's a force? A force is defined by Newton as being a thing, any action, some action that accelerates a mass. So if you have a mass, something that has mass, and it is accelerated, then a force must be applied to it. So if you start from speed 0 and you end at speed 60, you must accelerate from 0 to 60 miles per hour, kilometers per hour, miles per second, what have you. But it would be accelerated. So in order to go from 0 to 60 miles per hour, you need to accelerate it using a force. And if you wish to decelerate something, or negative acceleration, then you would also apply a force, which might be brakes or something like that, or a rocket engine going against the direction you're going, or a hand stopping something. So forces cause masses to accelerate or decelerate. And that is a property of this thing called mass. So if a mass is accelerating, then a force must be being applied. Now, acceleration is a strange thing, because we tend to think of it in terms of speeds, right? But now Newton then added the idea that it's not just speed, it's also direction. So an acceleration is in a given direction in addition to at a given speed. So speed is just how many meters per second is it changing every second. Like if you're accelerating from 0 to 60, maybe you do that over the course of 6 seconds. So it's 10 meters per second per second. That would be your acceleration. So that would get you up to 60 meters per second in 6 seconds, 10 meters per second per second. So, but let's say now you are keeping the same speed and you're starting at 60 meters per second and you start turning to the right. Now you're not going in a straight line anymore, so therefore you must be accelerating. And so the acceleration is also a change in direction at the same speed. So you can use that as an idea to derive planetary motion, because planets go in ellipses around. So they're changing their direction. Kepler said they also change speed, but let's for a second assume a perfect circle orbit, which we know from history doesn't really exist, but that's not the point. The point is, if you had a perfect circle and it's orbiting in a going around in that perfect circle, the speed would never change, but the direction would. So therefore a force is operating on it. If there's a force operating on it, what's the force? All right, so in addition to forces operating on things, you can't just have a force that doesn't push back. So Newton's third law of motion is equal and opposites. For every action, there is an equal and opposite reaction. For every force that is operated upon, there is an equal and opposite force the other direction. So when we think, wait a second, we set something on a table, the force due to gravity means if we pull the table out from under it, the thing would drop, right? So what is actually acting against the force of gravity? The thing that's acting against the force of gravity is the push by the table up. So you set something on a table. You stand on a balcony or something. The balcony pushes up against you, against your being pushed down by the force of gravity. So there's an equal and opposite reaction for everything. If you wish to accelerate a car to 60 miles an hour from 0, what are you forcing against? Well, you're forcing against the ground. The car is pushing against the ground. So what's the ground doing? The ground has to push against the car with the same force that the car pushes against the ground. So everything's opposite and reactive. And another way of looking at it, a classic problem you'll find in a college physics course, is imagine that you're on a flat lake of ice. And I grew up in Minnesota, so everybody always talks about going out in the ice in January. And so you go out in the ice in January, and what do you want to do? You get stuck. Maybe your car runs out of gas. You have people drive cars out onto the ice. So your car runs out of gas. So can you push your car off the ice? Now, this is a good question. Now, if you're wearing crampons, meaning like spikes on your shoes, then in theory you could, because if the rubber slides on the ice better than the crampons do, then all you have to do is overcome the friction across the ice. Now there's a lot of friction. Friction depends on the mass and the pull, so the car might be sinking into the ice harder than you can push against it. So, but in theory, you can push things around if the balance, if there's a balance, if there's an upward and downward balance against it so that there's no friction. So that's why we can think, oh, if you put on ice packs, how much friction does it take, how much push does it take to push across an ice field? But let's say there's no friction at all, and you just go up to the car, and you're both on ice, your tires are slippery and your shoes are slippery, and you push. Does the car move? And the answer is yes. You force on the car, and the car forces on you. But remember, the forces are equal and opposite, and the acceleration is dependent on the mass. So the lower mass thing, meaning you pushing against the car, gets accelerated more. The higher mass thing, the car on the ice, gets accelerated less. But they're equal and opposite. So the product of the mass times the acceleration for you is equal to the product of the mass times the acceleration for the car on the ice. The car is more massive, so it accelerates less, which is really interesting. So basically, yeah, you can, but it's going to go, you're going to have to push a lot, and you're going to be pushed away from the car far more than you will push on the car. So it's not practical to try to push your car off the ice if you're stuck out there after going ice fishing, and then you find yourself your ice shack. You need to go off and get some supplies at the corner store in order to make it through yet another cold Minnesota winter. So basically, Newton's 3 laws help summarize and understand how everything moves in the cosmos. Meaning, if there's a force acting on something, then it changes speed, it changes direction. Or, let's say you drop something. Let's say as you're moving and you're going at 60 miles an hour, and all of a sudden a big chunk of something falls off the car. Could that actually work? Maybe it's an acceleration. Maybe you have a rocket engine and that has mass to it. And as you expel the mass, you actually go faster. So if you drop the mass, you can actually accelerate faster too. Anyway, there's a lot of ways to do things like this. So those 3 laws encapsulate equal and opposites, F equals ma, and the rest and at rest of the definition of momentum. Basically, the first law is called a definition of momentum. And if a thing that has 0 momentum, the product of its mass times its speed is 0. And if you're going to change momentum, it always has it's a conservation of momentum. That's what the number 1 law really talks about. In any event, so the last one that he talked about is he said, all right, now, the planets. How do the planets go? The planets operate under a force that he called gravity. And gravity is a special kind of force. Now, how is it defined? He defined it as a fundamental thing. The force due to gravity is proportional to the 2 masses that are gravitating against each other, the product of their 2 masses, divided by the distance between their centers, squared. So the product of the 2 masses divided by the square of the distance between them is proportional to the force that they have to each other. So in order to actually know what that force is, you have to measure that proportionality constant. So frequently you'll see F sub g, or a force due to gravity, is equal to some constant, big G, which is Newton's gravitational constant, times 1 mass times another mass divided by the distance between them squared. So it is now this constant of proportionality, big G, not little g. Little g is the acceleration due to gravity at the Earth's surface, but big G is the measure of how strong the acceleration due to gravity is on a given mass. So let's say you have all these things, and that's Newton's positing that exists. He posits the inverse square law of the distance. He posits that the force is due to the masses and only their masses. So gravity operates over a distance. It operates only between masses. And that's really something very interesting. So when this happens then, remember we said that a force exercises on something if it changes direction. So now let's pretend we have a circular orbit. And Earth's orbit is almost perfectly circular around the sun. Almost. So it's a good example. So as the Earth goes around the sun in its almost circular orbit, as it goes around, we can actually say, well, what's the force that's causing it to go in that direction? So F equals ma is equal to the gravitational force, gmm over r squared. What are the masses? Wait a second. The mass of the Earth is in there, and the mass of the sun is in there. So there's an acceleration. how fast is the Earth accelerating? What is the change in the speed? Meaning, the change in the speed as it goes around the sun. Well, its linear speed around the circle doesn't change too much, but its directional speed does. Meaning it goes in this direction, then 4 months later it's going in this direction, then 3 months later it's going in this direction, and 3 months later it's going in this direction. So the direction of the speed is always changing. And so therefore a force must be acting upon it. All right, so we then equate these two and take into account their directions and play a whole bunch of algebra and math. And we find that this can actually help us get to the laws of orbital motion. Now, notice I said that the changes in speed, change in anything through time, is the basis of the calculus. And calculus is one of the branches of mathematics that everybody in college learns when they take physics classes, or it's one of the first things they take in the math major and so forth. Almost everybody in college who has to take a math class has to take a calculus course. So calculus is simply the way that we derive and measure changes of things with respect to another thing. So what are we changing in accelerations? We're seeing how speed changes with time. And speeds themselves could be looked at and say, how do we change distance with time? All right. Forces show how the acceleration, or forces dictate an acceleration. If the acceleration is constant, then the constant change of speed with time. So that also makes directions as well. So the calculus was a way of saying, how can we do these tiny changes in speed over time in order to show orbital motion? What's funny is that the concept of orbital motion and speed and changes was actually kind of thought out in very rough format by Galileo in his dialogue concerning two world orders, as well as by Kepler and many of his contemporaries. They all thought about this change in direction and change in speed as things go around. But they had a really difficult time formulating mathematically. Kepler's mathematical formulation was opaque. Galileo did not do a mathematical formulation of the calculus. He only looked at specific changes, but he did not go as far as Newton did and create a general set of rules and created the mathematics around the calculus so that other derivations could be done. Well, what ended up happening is that Kepler's laws, as a result of Newton's development of the calculus, were derivable from his three laws and from his law of gravitation. You can derive Kepler's p squared equals a cubed law straight from Newton's laws. It just falls out. The shape of an ellipse also falls out if Newton's laws are used, which is really quite amazing. So you can take Newton's three laws of motion, the calculus, and he derived to actually manipulate it, and what I would call the axiom, or starting point, or law of gravitation, where we just said the force due to gravity is this thing. So it was a definition. It's an interesting thing. It's a starting point. And you can actually derive Kepler's laws and show that all of these things occur. Well, the next thing we say is, well, we can derive the orbital masses and say, well, remember we had this thing where the sun was at the center of an ellipse, one of the foci of the ellipse, and the Earth went around the focus and the sun was stable and steady? That's not entirely true. What the two masses do is they orbit their center of mass. So Newton's law says because that they're always equal and opposite, that as the Earth goes around the sun in a very, very, very little sense also goes around the Earth. But so what does that mean? All right. So Newton's laws can say, take a couple of kids and put them on a teeter-totter, like a little balancing teeter-totter thing. And if one kid's bigger than another kid, then what do you got to do? The big kid's got to sit really close to the fulcrum of the teeter-totter, and the little kid's got to sit very far in the end of the teeter-totter. And as they, well, let's see, if the teeter center is here, and here's a big kid, and your little kid's here, so then as they go, the little kid moves up and down a lot to balance the big kid. So we can think of it in terms of lever arms. The center of mass between the big kid and the little kid is close to the big kid on the teeter-totter. So we got this teeter-totter thing. Now in space, there's no teeter-totter. You can go all the way around. So the sun's much more massive than the Earth. Therefore, since the sun's so much more massive, the center of mass is closer to the center of the sun. That's all it is. Same thing with the Earth and the Moon system. The Earth and the Moon, they orbit a common center of mass. That center of mass is inside of the Earth, just in the same way the center of mass is inside the center of the sun. So the sun's wobble as it goes around the center of mass with respect to the Earth is very small. The Earth's wobble going around with the Moon is much larger because the Moon's mass is large, and it's close to the Earth. So their center of mass is getting closer to the Moon. If you talk about something like the planet Pluto, Pluto and Charon orbit a common center of mass, and their center of mass is between them. So they go around like this. They go around each other. In fact, we know about binary stars, which we talked about very long ago. Two stars that are seen to be orbiting each other in the sky, and they orbit a common center of mass. So binary stars are seen to orbit common centers of mass, which is their balance point between the mass of them as they move. And the common center of mass arises out of the necessity of equal and opposite motions, as well as, specifically the equal and opposite motions. It creates the center of mass. And the center of mass then is the thing that might move as a group through it. So we talk about everything in terms of their center of mass. So the sun and the Earth orbit a common center of mass. The sun and Jupiter do. In fact, if we take all the planets and put them together, we can say the entire solar system as a thing orbits a center of mass. And that center of mass is in one place. And the sun orbits that center, so it's kind of wobbling around a little bit, because all the planets are very small. But Jupiter's pretty big. It's bigger than all the other planets combined. So as we look at Jupiter and all the planets, we see that the wobble of the sun is pretty big due to Jupiter. And when we look at variable stars later, we will find that this wobble due to planets can actually be measured and it can actually tell us the masses of planets around distant stars. And so we can learn a lot using that. And this all comes from Newton's laws of gravity, which were published in 1687, which is an astonishing thing. So Newton's laws tell us about the nature of this thing. But here's the thing. Remember that old parallax thing that came up? Now, Newton's laws are really important. They give us a framework, a mathematical framework, an easily used mathematical framework for discussing the center of the universe, discussing how things move. But yet, no one, not even Newton, none of Newton's contemporaries had yet measured the Coriolis effect, nor had anybody measured the parallax effect. So, is this all just smoke and mirrors? Is this real? Is the movement of the Earth real, or is it just a mathematical construct? And we'll look at that next time. See you. Hello, this is Jason Kendall, and welcome to yet another one of my introductory astronomy lectures. Last time I introduced Newton's laws, and I said all sorts of crazy things like equations like F equals ma and gmm over r squared, and showed them to you over on the side of the screen. But sometimes when people look at this stuff, they get terrified. So I want to actually get rid of that terror about equations and tell you what they are. So equations are really just shorthand versions of sentences, of very long sentences. So let's actually look at one of the fiducial equations that we saw last time, which is F equals ma. Okay, so now anyone who looks at this thing would say, oh, F equals ma. What's ma? Well, that's clearly not the way to write it. So F equals ma is just an extreme shorthand for what we talk about. So each of these things has a definition, right? So when we talk about m, we're talking about the mass of an object. The a is the acceleration, and f is the force. And so that's the definition of a thing. So really, these are shorthand notations. And when we say this, we'd say the force is defined to be a mass that is accelerated, or a force is that which accelerates a mass. That's another way of saying this equation. So, well, what does that actually mean? I mean, the thing is that science is about measurement. So when we talk about measurement, measurement is the key to everything. And so we have to say, well, what the heck are we measuring? Okay, acceleration is a change in speed. All right, so what is an acceleration? So we say acceleration is change in speed. So what do we mean by change in speed? This silly thing is not working as well as I need, so I'll go to that one. So acceleration is a change in speed. So we would say change, well, what's a change in speed? Well, speed, change in speed, is a distance divided by a time. A distance divided by a time is a speed. All right, so if we then say a distance divided by a time, how that changes with time, we would say a distance divided by a time divided by a time. That's really clumsy. But that's what an acceleration is. It is a distance divided by time, divided by time. Again, what do we mean by that? Well, let's say we have a speed. We'll call it speed 1. Go speed racer, speed 1. And then we end at speed 2. So there's our beginning speed is speed 1. Our ending speed is speed 2. Now then, we might have started our clock at clock 1, clock time 1, and we would have ended our time at clock time 2. Wow, well this kind of helps us understand what we're doing. So speed 1, speed 2, we want to compare the change in speed over the change in time. So we'd say, well, take speed 1 and subtract speed 2 from it. Now, if speed 2 is slower, we're decelerating. Well, in this case, let's say we're accelerating, then speed 2 would be bigger than speed 1. I mean, it doesn't really matter. If it's the negative sign, wherever it appears, just you have to remember it and follow it. So let's say speed 1 is lower than speed 2, right? So we end with a bigger number, so it's a bigger negative number. It's just going to be kind of weird, but let's see what happens though. So, and if then time 1 minus time 2. So those are our two times. So if we start from a small speed and go to a big speed, we get a big negative number. But time is like we start at 10 seconds and maybe we end at 15 seconds. So that's a negative number, so they cancel. So the difference in speed divided by the difference in time, that's an acceleration. Now whether it's accelerating or decelerating, we really don't care. So difference in speeds divided by difference in times gives us an acceleration. All right, so what does that mean even still? So we're going to get back to this F equals ma. We're going to try to interpret it. So here we go. But let's use this. Now, when we talk about speeds, when we talk about times, we have two sets of units for distance and time. They're two different things. Now, when we talk about Einstein later, we're going to make sure they're the same, but wait for that. So distance is a fundamental thing. And when we talk about distance, we might use meters. Okay, meters for distance. And time, we might use seconds, right? So a speed is simply a meters per second because it's a distance in a time. So what's the distance per time? It's meters per second. So a speed is meters per second. And a time is per second. So the units, that's weird. The units of speed. Units of speed. When we talk about units, we mean what we're measuring it in. We can measure speeds in meters per second, kilometers per hour, kilometers per second, miles per hour. That's a measurement of speed. And acceleration is speed per second, or miles per second, or meters per second, or kilometers per hour per second. That's a weird unit. But that's when we say, like you'd see a car commercial and they say, oh, this car can accelerate from 0 to 60 in 5 seconds. That's 60 kilometers per hour. It goes to 60 miles per hour in 5 seconds. It's 60 miles per hour per 5 seconds, which means it's, what does that work out to be? 12 miles per hour per second, which is kind of a weird unit of acceleration. But it is a unit of acceleration because it's a distance per time. So what do we have then for distance? Units of distance then are distance divided by time, or we can just say meters per second, because that's our standard. Our standard is the SI units, which are the Système International, or SI. So meters per second is a standard unit. So 1 meter per second is a speed of 1 meter per second. 60 miles per hour is miles per hour. We convert miles to meters and hours to seconds if we want. But let's just keep it simple and use meters and seconds. So an acceleration is meters per second per second. So that's meters per second squared. Exponents. So the units of acceleration are distance per time. I'd like to say it like that. The units of acceleration, what we measure in acceleration, are distance per time. Or we can say meters per second squared. You notice what I did there? Here's a scary thought. The units of acceleration are in meters, which is meters, and seconds, which is seconds. Meters are meters, which is a distance unit. Seconds are a time unit. But look at F equals ma. What's that m? M is mass. Oh, we're going to drive people crazy. We mix up units and definitions. So we have to be careful. We have to be very careful. Every number has a unit associated with it in science. If you make a measurement, you make a measurement with some kind of unit. So we were talking about distances. Okay, we can say that a speed might be 60 meters per second. So there's a 60 m divided by s, 60 meters per second. So if we have 60 meters per second, then that's our speed. But notice the m in meters is not the same as the m in F equals ma. I know, that's annoying. But guess what? We got to live with it, and we got to learn when we use an m as mass and when we use an m as meters. All right, so in a general equation like this, where there's no numbers attached to it, generally in equations, the letters in it can be independently multiplied together. This is mass times acceleration, not the word ma. Mass times acceleration with the cross for multiplication implied. So F stands for the word force, M here stands for the word mass, and here is this. And when we use this, we call this Newton's law of acceleration. But when we use this, we're making a measurement of speed. So we might say speed equals, right? So we say speed equals 60 meters per second. And we'd say, wait a second, we're going to vary from 60 meters per second up to 200 meters per second over the course of 5 seconds. So the acceleration would be 120 meters per second minus 60 meters per second divided by, maybe we do that in 10 seconds, 10 seconds in terms of 10 seconds. So then we end up with 6 meters per second squared, because the seconds go on the bottom, and that's how the algebra works, is that these seconds go to the bottom, that second goes to the bottom, they're a product, and we get a set meters per second squared. So the end result is that the units have an m and an s squared, but the m is shorthand for meters, and this s is shorthand for seconds, and that is not the shorthand for meters, that's the shorthand for mass. So these are separate objects. Notice this is not a measurement. F equals ma is not a measurement. It is a statement of relationship. Whereas this is a statement of measurement. Speed equals 60 meters per second. So if we have some statement of measurement, there shall always be some units associated with it. The standard units for almost all the measurements that we're going to be talking about in the system is SI units. The distance of the unit of distance is the meter, which is abbreviated with a little letter m. There's also a derived unit from it, which is the kilometer, which has the abbreviation km. So there's 2 letters together. And it doesn't mean it's k times m, it means it's kilometer, which is an abbreviation for a unit. So we don't use kilometers in here or anything like that. That's not a statement of relationship. This is a statement of relationship when the F equals ma. But now I'm talking about statements of units, which are when you take a measurement. So you might measure a distance in kilometers, but you're not going to always write out the word kilometers, right? So you write the little letter km. All right, we've also have other measurements of distance, such as the astronomical unit, which is a huge number of kilometers. It's 150 million kilometers. Now 150 million kilometers It's a long way. And we don't want to have to always write that out when we're talking about the distance between the Earth and the Sun, or between Jupiter and Saturn, or between Saturn and the Sun, or between the Earth and the Sun and Pluto. We don't want to write 600 million billion kilometers or whatever it has to be. We want to just say for distance to the Sun is 9 astronomical units. The distance to Neptune is 40 astronomical units, or whatever it happens to be. So that's what we want to focus on, is those easy to use units. You use the units that are easiest to use, but that doesn't change the relationship. F equals ma is a relationship between forces, masses, and accelerations. You can use whatever units you want in acceleration. You can use whatever units you want in mass. There's a standard unit for force, so you might as well use it. And therefore, your unit of mass that we use is called the kilogram, not the gram. A gram is about as much as a paper clip or two, or a penny or two. But the unit of mass is the kilogram. The unit of distance is the meter, the standard unit of distance, and the standard unit of time is the second. So those three things give us pretty much everything we want. Everything else is derived from them. So distance is a fundamental measurement, time is a fundamental measurement, mass is a fundamental measurement, speed is not. Speed is derived by taking a distance over time, measuring a distance through time, like how fast are you going. An acceleration is how fast do you change how fast you're going through time. That is a derived measurement based on distance and times. So then we can say, well, if we take a given mass of a certain number of kilograms and accelerate it, we must have been applying a certain amount of force. So if we take 10 kilograms and accelerate it 60 meters per second squared, right? So 10 times 60 is 600. We must have applied a force of, what's the unit of force? Well, because Sir Isaac Newton developed the concept, we call the unit of force a Newton. So 1 Newton is called a kilogram times a meter divided by a second squared. It's a very strange unit. Remember, this is a mass times an acceleration. So masses are in kilograms and accelerations are meters per second squared. So when we look at the nature of what a force is, the force in terms of units is meters per second squared. Now we can have another derived unit, and that could be called energy. Now there's a lot of woo-woo stuff about the word energy, and what is energy? Energy is this and that, and it creates us, it forces, the force binds the galaxy together, whatever. But energy as a thing is an odd concept. But we can define it fairly simply for our uses in the material world, because what we want to do is want to see how much energy does it take to exert a force. Because when you exert a force, notice that if you exert a force and let's say you're pushing something up a hill, you're using a lot of force. Now, where does the force come from? The force, the act of accelerating a mass through a distance means that you're exerting you're exerting energy. So exerting a force and using energy. So energy is being applied from one thing and being used to do another thing. So energy has an interesting set of units. It's kind of like this, but energy is force times distance. So a force applied through a distance is a unit of energy. So if you remember last time we talked about pushing cars across the ice, so you have a force pushing it, maybe you actually get the car to move a few meters, and it accelerates over the course of a couple of meters, over a course of 2 meters, you accelerate it from 0 to 1 meter per second. You're doing a pretty good job if you do that. You accelerate a car from 0 to 1 meter per second on ice over the course of, say, 2 meters. You hit it pretty hard, I think. You probably did. So the energy that it took is 2 meters, which is the distance through which you applied the force, times the force that you did, which is a mass, the mass of the car, whatever it happens to be, big, maybe 2,000 kilograms or 4,000 kilograms, a 2-ton truck. So 4,000 kilograms times the acceleration, which is 1 meter per second squared, times the distance through which you did that, which is 2 meters, and that's kind of a weird thing. So let's write that out so we see what we have. And let's see, I hope this is all actually getting read on there. Find out when the replay. So if you have energy through an energy as applied by a force, or we will call this particular kind of energy work. And work is defined very specifically, meaning you take a force and you apply it, you multiply it by the distance through which you do it. So you take a force and you push something for a certain length of distance. Now, that's kind of an interesting way of thinking about it. It's a force applied through a distance. So you could say, well, I'm pushing on the truck and I have to keep my hands in contact with the truck. How far did I go while I did that? And that was 2 meters. So the force that I exerted on the truck was 2,000 kilograms that I accelerated for up to 2 meters per second. And I'm sorry, I said 1 meter per second, right? 1 meter per second. And I applied that force for 2 meters. So I went like this. So the length across here is about 2 meters. I pushed, released. So as I push on it for 2 meters. The car is, well, now it's a little car. It's one of those half a smart, like a little bit more mass than a smart car. 2,000 kilograms, and I accelerated it at the end of the acceleration. It was accelerated 1 meter per second. So 1 meter per second, sorry. So I accelerated it 1 meter per second squared, and at the end I kept that push happening for 2 meters. Now that's a heavy push. That's a really big push if you think about it. If we multiply that all out, that works out to be, whatever the units are, is 4,000 of something that has the units of kilograms times meters squared divided by seconds squared. Now that's interesting. So there's a mass in there, there's 2 distances, and there's 2 times. Kilograms times meters per squared divided by seconds squared. If we look closely, that looks like a mass, which I'm now going to do in capital M just to say it's a mass. I'll just write the word mass. Times a speed squared. Times the square of a speed. So another way to think about it is, now that the car is moving, I've pushed it with that movement, now it's sliding across the ice. It has energy of motion. How much energy of motion? Well, how fast is it going? It's now going 1 meter per second because that's the acceleration that I pushed it up to. I pushed it up to, well, I went 2 meters. I don't know how long it took for me to do that. So let's assume at the end it was going 1 meter per second. If I applied my distance for 1 second across it. So let's say it's going 1 meter per second, and that's the total energy it ends up with. And so therefore its speed is 1 meter per second squared, which is 1 meter squared per second squared, and times its mass, which is 2,000 kilograms. It now has a lot of speed. It has an energy according to its speed. And if you don't believe that, just let it hit you. So you get out of the way of a car sliding towards you, because when it hits you with a lot of energy. So energy is this thing that we call the thing that can make things move. It's an odd way of thinking about it. Energy is a thing that can cause forces to be acted. It is also a thing that causes motion. It is also something that possesses, that you have when you possess relative motion. Like if you're right beside the car, both you and the car have energy, but you're right next to it. Or maybe you're inside the car. Do you have energy with respect to the car inside the car? When you finally hit the other side of the lake from that icy lake, yeah, you're going to feel it. But the point is that energy of motion, which we call kinetic energy, this energy of motion is mass times the speed squared, but there's also energy which we call work, which is applying a force through a distance. So there's these funny things. So to summarize this little bit, we have 2 ways of looking at equations. The first one is there's an expression of relationship, force equals mass times acceleration. Another expression that we learned last time was the expression due to the force of gravity. And how does that look? Well, the force due to gravity, which is a special kind of force, and so we always put a little sub g underneath it for gravity. that is equal to some big number, capital G, times the mass of one object times the mass of the other object, divided by their distance, divided by the distance between them, squared. So now I've used new letters, haven't I? But yet, remember, as I was writing it, I was giving you a description of each of them. I called this a force. I said the force due to gravity is defined to be, and that's what the equal sign means. It means it's defined to be this some number, big G, which is an experimentally verified number. You can't derive it from anything. It's just a number of nature. It's the relation, it's how the masses translate into a force. So if you have some mass, say the mass of the Earth, and you have some other mass, say mass of you. You are pulling on the Earth and the Earth is pulling on you. So between you and the Earth, and what's the distance between the center of your mass, which is somewhere in the middle of your gut, and the center of the Earth, which is thousands of miles below you. So mass of you, mass of the Earth, divided by the distance between your centers of mass, times this mystical, magical, weirdo number, capital G, which is derivable only by seeing the acceleration, knowing the distance, and knowing the masses accurately. Can we get this gravitational number, which is a constant of nature? So this is a measurable, meaning the mass. This is also a measurable, meaning the mass. This is a distance, which is a measurable. And this is a force. So remember, a force is equal to a mass times an acceleration. But on the other side, we've just got two masses and a distance. So this crazy number G takes care of the rest of the units. So it has very strange units that convert mass times mass divided by distance squared into a mass times an acceleration. So units are important. When we say units, we mean how we measured the number we're talking about. And in if you're doing a regular math class, units are not important because in geometry they are, but in just like algebra, like ninth grade algebra, you don't necessarily attach units onto solving equations like y equals x squared plus 4x minus 2 or something like that. You don't propagate the units of there. You're just finding the relationship between x and y in the algebra class. But in everything in science, no matter what we do, we must associate with every number we measure what it is we're measuring. We're measuring kilograms, we're measuring meters, we're measuring meters per second squared, we're measuring pounds of force. If a pound is a unit of force, which is the gravitational force. So anything that we measure with a unit, and in science there always is a unit attached to a number. Always. There are some numbers that are unitless, which are very strange, but yet they're associated with the sciences, and they're conversion factors between one set of units and another, or they actually play into a measuring system. But in every possible measurement, everything that we measure has a unit, no matter what. So that's science. It has, we say, this number of things, like 12 oranges. That's a measurement of how many oranges you got. So in science, we have expressions of relationship. F equals ma, gmm over d squared. These are expressions of relationship, how a force is defined, how the gravitational force is defined. Those are expressions of relationship. And then we have a different kind of thing, which is the solution of the relationship given measurements. So we measured the amount of force. We can actually get the force measurement from, let's say we go to the model rocketry store and we get model rockets. I did that when I was a kid. A lot of fun. Get a model rocket, it tells you how many newtons of thrust it has, and you attach that in there and says, oh, it's how many newtons of thrust, and it shoots when you ignite it. Maybe the rocket will blast and keep blasting, and maybe we'll see how much energy it emits by when the rocket goes, not just how long it takes for it to ride, but how far it pushes, and that'll determine the output of energy that it had. Or we can say, how fast is it going when it gets up to its maximum energy? So it went from 0 to 60, say, or whatever, how fast it goes. And so the mass of the object that's been accelerated and now it's going a speed has acquired energy. And so we manipulate both of these. And here's the trick. We manipulate both of them using the laws of algebra. So that ninth grade algebra thing, whether we're talking about relationships between equations, meaning fundamental relationships, what is a mass times acceleration, or different kinds of forces. There will be lots of other equations in science, and we're only going to talk about for this class, for this set of lectures, only a very few numbers of them. But these expressions of relationship follow the same rules of algebra as when we multiply numbers together. And in fact, if you looked really carefully, you'll notice that I applied the same rules of algebra to units. I have a mass times a mass, so I've got a mass squared. That's m times m. Well, m is meters, not masses. So when I took a meter measurement, a distance measurement, and I said, okay, meters times meters is meters squared. That's algebra again. So we can apply algebraic principles to unit measurements in the same way that we apply algebraic principles to these as well. They're linked, they use the same ideas, but your problem that you're going to always find in science, no matter how you do it, is trying to say, break yourself away. It's very difficult for a lot of people to do. And for me too, for a long time, it was tough. Because, you know, I like to read, and I read a lot of different things. So when I read this, I would say F equals ma. Well, it's not ma. It is a force is defined to be something that accelerates a mass. Every equation that states a relationship is a shorthand thing for a long paragraph of chatting. So when we talk about Newton's law of gravity, again, it's a relationship that describes that defines how the force due to gravity operates. So the force that accelerates a mass is defined to be the product of the two masses that are gravitating divided by their distance squared. So that's the definition in words. So you don't read an equation like ddmr squared or something weird like that. You read it as a sentence or as a short paragraph. They're shorthand equations. So in that sense, equations are very much like shorthand, like a stenographer would write when they're trying to write really fast things, and say like a court stenographer. They have a shorthand notation that is defined sets of words that define shorthand notation that defines words and paragraphs and whole sentences. So in that sense, this is a very beginning idea. I just want to give you a cautionary way of thinking about it and saying that there are equations and every measurement has units and every unit has values. So I'll show you where you can actually derive those things at the end of the video. Hopefully I actually remember to do that. So at the end of the video, I'll show you a place where you can actually go see many of these things, and I'll show you a bunch of Wikipedia pages that are worth looking at. So we'll see you next time. Hello, my name is Jason Kendall. Welcome to yet another one of my introductory astronomy lectures. Last time we did a little bit of a side diversion over to the nature of equations and things, and I provided a bunch of references. But really, to finish off the whole thing, we need to start where we began. If we go all the way back to Aristotle and the debate of the ancient Greeks about who's in the center, the sun is at the center of the cosmos, or is it the earth that's the center? And this was a subject of debate for centuries. So really, this deserves its complete answer as to what the resolution of the whole thing is. All right, so is the earth actually moving, and do we have actual evidence there too? Yes, we do. Simple statement, but let's actually show you the measurements that we're talking about. All right, so the big bugaboo for everyone was parallax. If the earth was moving around the sun, there must be parallax. And even after Newton published his Principia, the laws of gravity, the laws of motion, the parallax still had not been observed. So it was an area of active research. In 1674, Robert Hooke tried to do so with Gamma Draconis, which is a bright star in the constellation Draco, which is easily measured in London because it passes straight overhead. And so what he tried to do is he tried to actually see the parallax of that star, and he wasn't entirely successful. So, but at least paved the way. And in 1725, James Bradley set up a special telescope that was basically inside a big chimney, and he hunted for the parallax of Gamma Draconis. Because he was also in London, he wanted to make sure he could actually do this. And he actually then also looked at other stars as well that passed through his telescope, because it was a fixed point telescope. And he found another star, 35 Camelopardalis, which is another star that passed through the field of view. He did not find the parallax. However, he found something else that was even stranger. Because he was trying to find parallax, he was trying to find the annual motion, the annual change of the position of a star as the Earth was going around. So every star should have the same kind of parallactic motion if it's in the same direction of the sky. But what he found was that Gamma Draconis had this very strange motion. Well, over the course of a year, it would drift a little bit southward and then drift back to center and then drift a little bit northward and then back. And this drifting was because, initially he thought it was parallax, but if he waited a certain period of time for the star 35 Camelopardalis to actually come also into view, he found at the same exact time, maybe a few hours later so it could get into view, that Camelopardalis actually at the same time that 35 Camelopardalis, which I'll call 35 Cam from now on for make it easier, and Gamma Drac for the other one, was actually drifting the other way exactly at the same time. So as Gamma Draconis was drifting southward in the telescope as they were hunting for parallax, 35 Cam was drifting northward, but just by a little bit, not as much. And they actually swapped places. Now this was really strange because it's like, well, this can't be affected by parallax either, so maybe it's something in the sky, maybe I've got some problem with my telescope. But what ended up being is that in 1728, they actually discovered the motion of the Earth in the following way. This is called stellar aberration. And we can think about it in the following way. The shift that they saw with Gamma Draconis and 35 Camelopardalis, with Gamma Draconis being the biggest effect, was the idea that imagine your telescope is a long tube. And what you want to do is you want to hold the tube in such a way that, let's say you want to run in the rain. So you're going to go running with a tube in the rain, and your goal is running in the rain is to make the drops as they're falling, as you're running with the tube, not hit the sides of the inside of the tube, but only the bottom of the tube. You don't want the sides of the inside wet, you only want the bottom. So as you run in the rain's coming straight down. As you run, you've got to tilt the tube slightly so that as the rain falls in the tube doesn't touch the raindrop as it moves. Now if the tube's still, you could just hold it right in place and go thump, 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 thump right to the bottom and not hit the sides. But the tube is moving to the side. As the rain comes into the tube, it'll hit the side before it gets to the bottom. So you have to tilt the tube slightly. Now, if the telescope is already tilted, then what you find is that, wait a second, the tilt of the telescope happens because you have to change the position you're looking for to center it up slightly, because as the Earth moves, it takes the telescope with it. And over the short period of time that the light takes to travel along the length of the telescope tube, the Earth moves and pulls the telescope with it. So you have to adjust for that in order to center up the object inside of your field of view. So the apparent position of the star changes because it changes where it lands on the detector at the back of the telescope. So the telescope moves, the light falls down like a ray, and instead of hitting the bottom of the telescope, which would mean where your detector is, it might hit the side. So you have to you have to literally change the angle of the telescope in order to keep the star centered. And that can only happen if the telescope is moving. So if we know that the laboratory has a telescope that's fixed with respect to the Earth, then in order for this change in position to be taken into account of, because of this movement, like trying to catch raindrops in a bucket and not get the sides of the inside of the bucket wet, then the telescope must be moving to a certain given direction. And the change in north-south direction is a result of the position of the Earth's direction of motion at the time of observation that James Bradley was doing this. And if you wait a few hours later, the Earth is going in a slightly different direction because of the rotation of the Earth, And we actually then discovered the motion of the Earth through space. And this motion is called stellar aberration. Basically, you have to point the telescope in a different direction to take into account the fact that the Earth is moving. Another way to look at it is, if you're driving into a snowstorm, the snowflakes appear to be coming at you straight on. Now, you know that they might be coming straight down. Maybe it's a perfectly still night and the snow is coming straight down, or the rain's coming straight down. But when you're driving into it, it appears to be coming towards you. So so that's an effect. The change of position of the angle that it's coming is a result of your motion, not the motion of the star. So as the car moves through the snowstorm, the snow appears to be coming towards you, even though in reality, if you were on the side of the road watching the car go by, the snow would be coming nice and straight down. So what we find then is that the discovery of the motion of the Earth through space was done in 1725 as a result of looking for stellar parallax. All right, so that was a very difficult thing. But now let's actually keep going with this. In 1791, an Italian mathematician by the name of Guglielmini actually measured the Coriolis effect. So if you can either have the Earth going through space, but is it rotating on its axis? Is it actually rotating? And if it is rotating, then yes, as something that's dropped off a tower should deflect. Or if something is shot out of a cannon northward, it should deflect. So there was a prediction based, if the Earth's rotating, how much deflection there would be if you dropped it, say, 30 meters down a spiral staircase or down a tower. What's the deflection that happens when you drop something? And Guglielmini did this thing. He tested a 29-meter drop inside a tower at the University of Bologna, and what he found was that there was a 4-millimeter deflection that always occurred to the east, as expected by Coriolis effects. So he discovered the Coriolis effect in 1791, thus proving the Earth rotating. Now we can use a Foucault pendulum, and you can actually make a pendulum go, and the pendulum will always stay in the plane that it goes and slowly rotate around the axis of the plane of rotation as the Earth rotates. It's another way to detect it. The other way is to go up in space and see the Earth rotating. That's another way. So the Earth's rotation can be measured on the ground using the deflection of things. Also, this was something that had to be taken into account in the Second World War, because as people had very long guns, the Navy could shoot these long shells many miles. As they shot northward, the shell would deflect. And so they had to take into account the Coriolis effect due to the flight of the projectile, the flight of the bullet, the flight of the projectile as it was going towards the enemy ship. And so you had to actually take that into account by given the distance, how much deflection it would be, and whether you're pointing straight north, straight south, a little more east, a little more west. So that had to be calculated so you'd actually hit your target, because the shot of the shells was so incredibly far. But they had to actually take into account Coriolis effects in the Second World War. But the first detection of Coriolis was in 1791. Well, what about parallax? Parallax was kind of the gold standard for Aristotle. It wasn't detected. Tycho Brahe said it wasn't something it could discover. So how did people actually find that? Well, there is a star named 61 Cygni, which is a binary star in the constellation Cygnus that passes overhead in the summertime for us. And it's a good candidate for looking for parallax because it's got a very large proper motion. The proper motion of it scoots it across the sky. Proper motion, if you remember, is the apparent change in position with respect to the background stars due to the actual motion of the star through space. So proper motion makes it look like it's going across the celestial sphere. And that proper motion, if it's large, that means it's got to be close. So people go, that's a close star. Maybe we can get its parallax. And so in 1838, Friedrich Wilhelm Bessel measured its parallax to be 0.285 arc seconds, which works out to be about 3.5 parsecs, or about 11.4 light years. So the very first parallax that was discovered was less than an arc second. It was a quarter of an arc second. It's an incredibly difficult measurement, and it took until 1838 for someone to develop it. So we really can't fault Aristotle or Tycho Brahe or anybody else who used the argument that parallax did not occur to shoot down the idea that the sun was at the center, because parallax was an extremely difficult thing to measure. Also, Coriolis effect was something that Aristotle knew about, and he couldn't detect it. But remember, it took until 1791 for someone to be able to make a tower that's over 30 meters high, that's 100 feet, and drop something, and then be able to measure the accuracy of the drop to within a millimeter. So you can see a deflection of 4 millimeters as something drops 29 meters. That's hard to do. Wouldn't expect that Aristotle and his team or anybody be able to do that until we could actually isolate things and do better with technology. Basically, 1791 technology was needed, which is not a lot, but just enough. And in 1725, the detection of the Earth's orbit, the Earth's motion through space, was done by hunting for parallax, but instead discovered stellar aberration, which is the effect of having to move your telescope in a different way in order to center the object, given where the Earth's orbit is around the sun. So if the Earth's orbiting around the sun, then the speed with which it's going in the direction towards that star changes the direction you have to look inside the telescope. And so these are very small measurements to make. They're very difficult, and so we cannot fault the ancients for not doing that. And we can also, so that what that meant is that Aristotle wasn't wrong. What he was he didn't have the technology to see it. And so these long arguments against the Earth being moving through space took a long time in order for the technology to catch up so that you actually see them. Stellar aberration is even a very difficult thing to measure. So is parallax. So is Coriolis effects. These things are hard to measure. So the initial measurements were extremely important to do. So once we finally did that, we can now say that yes, the Earth does rotate. And because of the Coriolis effect that is seen to happen when we shoot projectiles a long distance north or south. We also see it when you drop something. The Coriolis effect was predicted, but it's extremely difficult to measure. And so as you drop something, a very high effect, the Coriolis effect should occur, and it's a course of 4 millimeters over 30 meter drop. It's very hard to measure. And then parallax was finally observed to prove that the Earth changes its position around the sun and not the sun around the Earth. So people that think that the Earth is flat, people that think that the Earth is at the center, they're dead wrong, and they're wrong because we can measure the things to actually be true. And they're measured on the surface of the Earth, and these measurements apply to the cosmos. That is the power of this method of inquiry that we call science. The method of inquiry we call science says, give me your idea, give me your prediction, I'll see if it's true. If your prediction is falsified, if I make a measurement that falsifies your prediction, then your idea is false. So, but the thing is that people didn't have the ability to do certain kinds of measurements until very much later. So we then get to a point where there's a bunch of people who have the capacity, ability, and time and technology in order to accomplish a task of measurement. And then we have a group of people that can then establish what that is. And that's kind of the story of modern science. Modern science veers away from logical constructs that can be talked about relatively quickly, and it goes into detailed measurements that then support ideas that are tricky to get a hold of. So the reason I went with such a long time about this whole idea about does the Earth move is that when we talk about how old the sun is and what will the sun become when it's ancient and dies away, what is a black hole? What's a neutron star? How do we know the age of the cosmos? How do we know how big the galaxy is? These are extraordinarily difficult measurements to make. But the key is that when Bessel made his measurement, he told people how to do it. And people have replicated that measurement. And when Guglielmini made his measurement of the Coriolis force, he told people how he did it, and people replicated it. And when James Bradley published it in 1728 of exactly how the stellar aberration worked, he published it and told people how to take it into account. So that's the difference. People make measurements in science in order not to say, hey, this is this really cool thing I've discovered. They make the measurements to say, I know that I might have gone wrong. Show me where I made my measurement wrong. Show me where my ideas are wrong. Because this is my idea, and here's my prediction with this idea. Here's my measurement. Does it fit that? And maybe I did some bad measurement. Please go check. The point of announcing a measurement isn't that you're supposed to say, well, it's done now. I'm the person. I'm the authority. No, you make a measurement so that other people can go check you. And that's the key to science. It says, I know I could have made a mistake. This supports that idea. This refutes that idea. It supports or refutes some idea. Please go check. And here's how I did it. So here's what I hope you can do too, so you can replicate my results. That's the essence of science. And that's what grew from Aristotle to Ptolemy. That's what created the incredible difficulties of the Renaissance and the transition out of medieval thinking into Renaissance thinking, into modern science, and everything else that we're going to be talking about for the rest of this course. Details, ideas, just like that start from these really hard-won concepts. And now we run with them, where we say, here's my measurement, and look at this amazing result we got. And astronomy probably has some of the most amazing results and some of the most amazing measurements of all of human history. And we'll talk. Hello, my name is Jason Kendall, and welcome to the next of my introductory astronomy lectures. Today we're starting the discussions about light. Light, that thing that comes from the stars and comes to us and that allows us to see things. So what is light? Well, I'm going to get to the history about that in a later episode, probably the next one. But what I'm going to do now is just posit to you and tell you what the current state of thinking is about light. Well, we need to actually understand what we mean by this thing called light, and we're going to discuss it in a certain framework. All right, the first way we're going to discuss things is about there's two natures to light in the current way of thinking about things. Light can be exhibited both as a particle and as a wave. So what does that mean? Okay, well, waves are things that are phenomena in a medium of some sort. And we think of water waves as a good way of looking at it. But let's actually take a step back and say that we have a lot of evidence that tells us that light behaves in a manner like waves. And I'll discuss the history of that next time. But let's actually look at what we mean by waves and what are waves and so forth. Well, light has frequencies. Light has wavelengths. Light goes at a specific speed. So let's actually put all that together. Now, when we look at the nature of what light is, there are versions of light that we call visible light, and that's the light that we see with our eyes. It's an extraordinary narrow set of wavelengths from about 4,000 angstroms to about 7,000 angstroms, but yet light can have many wavelengths from extraordinarily short, much shorter than 4,000 angstroms, to extremely much longer than 4,000 angstroms, even till up to a mile or so. So the wavelengths of light can be as small as smaller than the diameter of a nucleus of an atom to larger than a mountain. And they're all light. So what is this thing that we call light anyway? Well, we'll call it electromagnetic radiation. So anything that is light, that is electromagnetic radiation, of which light, which we call visible light, is a very, very small part. So electromagnetic radiation is this thing we call light at any wavelength, at any frequency, not just the visible light. All right. So wave phenomena, what's a frequency, what's a wavelength, etc. Well, what's wave motion? So a wave motion, we can start with the idea that maybe we have a surface like a pond or something, and maybe we've got a nice little pond, and then somebody drops a rock into the pond, and that causes a wave to propagate outward. So a wave can be propagated as a propagating disturbance in a medium. So the wave propagates to the right, away from where the rock went into the water. But basically, this pattern of waves, maybe it's not like a continuous wave. Maybe it's just a brief piece of a wave. Right? So we got the water wave now. We drop the rock into the water, into the still water, and it makes a pulse. Right? And that pulse then travels this way. And that's what we see when we think about water waves. It like drops into water and it pulses and travels to the right. But let's now posit that instead of a rock, maybe we dip a stick into the rock, maybe like a stick with a ball in it, or maybe this. You take your fist and you just slowly go up and down into the water and make a continuous set of waves, or just tap the surface of water with your finger. And you can do the same thing. So then what do we get? Well, the disturbance in the water then looks more like this, right? It has peaks and valleys and peaks and valleys. Now, if your finger touches it, say 1 time each second, well, that's the frequency with which you touch it. So the frequency, there's 3 things that we're going to talk about with respect to wave motion. We're going to talk about their frequencies. There goes the shock. There goes the frequency. We're going to talk about their wavelength. And we're going to talk about their speeds. So there's 3 things. The first thing is frequency. So let's say in this example, we touch the surface of the water 1 time each second. Then the frequency of that interaction will be 1 touch per second. So frequency has units of number of actions per second. So maybe we have 1 touch per second. Maybe you're really twitching it like 10 times a second, right? So these are 10 times per second. 10 times what? 10 touches. Maybe 10 rocks are falling into the water each second. Maybe 10 automobiles are falling into the water each second. Those would be big waves. But relates to another 4th thing we have to look at is amplitude too. Amplitude. Because, I just described something which will give different amplitudes. So frequency, speed, and wavelength are all set up together. So now, what's the wavelength? Well, the wavelength is dependent upon the speed. So let's say we touch the water 1 time each second, and that wave goes out with a very, very long wavelength. Maybe the wavelength is extraordinarily, maybe it's a foot, right? So maybe the wavelength is 1 foot, right? Wavelength is measured in distance, is a distance. But what is the distance of wavelength? Well, the wavelength is the distance between 2 consecutive peaks. So we'll call that the wavelength. And the wavelength frequently uses the Greek letter gamma. Lambda, I'm sorry. Lambda is our wavelength, or W, but frequently lambda. Frequency uses the Greek letter nu, like, oh, I knew you were coming, or, oh, that's not a small moose, that's a new. Actually, GNU is GNU, and nu is KNEW, but this Greek letter nu is just NU. So the Greek letter nu describes frequency, the Greek letter lambda describes wavelength, and frequencies are always something per second, and distance is a wavelength, so it could be meters or yards or miles or whatever. Frequencies can be per hour too if you want, but frequently we're not going to use that. We're going to almost always use seconds as our time interval. So then we can make a speed out of them, because the speed of the wavelength depends on how fast the peaks of the wave are traveling to the right. So let's assume they're traveling that way. So the speed then with which they're traveling is simply equal to the wavelength times the frequency, or lambda times nu. So that will be something. So we could say, what's the wavelength? 1 meter. What's the frequency? 1 cycle per second. So what is a cycle? Well, oh, wait. What do we mean by frequency then in this diagram? Well, wavelength says, what is the distance between peaks? And the frequency then says how fast, how often per second the whole cycle occurs. So from here to here, or from here to here, what is the time interval? And time interval of travel. So we could say, maybe it takes 1 second for that to travel. Maybe it takes 1/10 of a second. Maybe it takes 1,000th of a second. Maybe it takes a year. Those would be long wavelengths, or at least very slow speeds of waves. So the wavelength is this distance, and times the time gives you the speed with which the wave is traveling through the medium. So that's kind of what we're thinking about. Now, amplitude is different. So what is amplitude? Amplitude is this. Is it a big wave or a little wave? And so big waves have high amplitude. So this would be a low amplitude, this would be a high amplitude. Amplitude is the height of the wave displaced from the medium. So let's say the lake is extremely glassy, right? and it's just really flat. And you drop a little pebble in. The amplitude from the wave is going to be low from the pebble. Now you drop a really big rock in from a very high altitude, on a cliff or something. And like some beautiful places where I've seen that. Anyway, you drop the rock off the cliff, you make a really big wave. So the big amplitude versus the little amplitude depends on the force of the disturbance that you push into it. So there are four basic things, although there is no relationship necessarily between the frequency, wavelength, and speed and the amplitude. The amplitude is separate from it, but part of it. So these three are related, but the amplitude isn't necessarily related to those. So in fact, it frequently isn't. You don't have to have a relationship between them. But that's our basic relationships of wave motion. So a wave can propagate through water, it can propagate through air. How you're hearing me is that as I speak, my vocal folds change in speed and they push on the air, and the air is compressed. So it's a compressional wave that reaches from me to the microphone, and therefore we get, you hear sound. Sound doesn't have a medium that goes like this, it's a pressure wave going towards you, so it's a little like car pressure. Another example of a wave motion is if you drive down a highway, and cars are not uniformly distributed on a highway. Cars tend to bunch up, so we can look at those as density waves, and how far are they apart? Well, you can probably find if you fly in a helicopter that waves of cars or groups of cars are separated maybe by half a mile or a mile or a kilometer if you wish. So they tend to be separated. And then when you speed up and go through the empty part, you get to the backside of a density wave, you have to slow down and go through it. But the density pockets drive as a unit. So we can look at lots of different things that approximate wave motion. Now, this all leads to a really fascinating set of ideas, because when we look at light, there's a lot of reasons to think that there's wave motion to light. So one of the earliest difficulties that people had with respect to light is, what's the medium for light? Because we know that, well, in air, a sound travels through air, and if there's a vacuum, sound doesn't travel through it because there's no atoms for it to press upon. So if there's no atoms to push against, then there's no sound wave, there's no pressure wave. If there's no pressure wave, there's no sound, and you don't hear anything. So what about sound waves that happen by hitting a surface? Okay, when I hit the surface of the chalkboard, what happens is that the chalkboard itself vibrates, and if you were to touch the wall on the far side, you'd actually feel the motion of it. So there's a sound vibration that goes through it, and that's partly compression, but mostly because it's on the surface here, it would feel more of an up and down thing. So actually the chalkboard itself vibrates a little bit when I hit it. If I hit it too strong, then I make a hole, but otherwise I make a little vibration. So wave motion happens in a flexible medium, or some sort of elastic medium that comes and goes and will restore to itself. So what is the elastic medium of light? Became an incredibly important historical question. But to summarize what we really want to look at for the nature of light as we know it, we know that light has a wavelength, and that wavelength has a frequency. But the funny thing is that for all light, specifically in a vacuum, but if you go to different media, it has different speeds. But the speed of light in a vacuum, we call by the letter c. So frequently when you talk about speeds of wave motion, you use the letter c. And if you study other areas of physics, you'll also see this, but it'll probably tend to be c sub s, which would be sound speed, or maybe other kinds of speeds. But the speed of light universally across all of physics is labeled with the letter c. And this has a unique value. It has a unique value of approximately 300,000 kilometers per second. All light does, in a vacuum. So this is a unique value. So it's approximately that. It's a little bit less, it's like 299, but we can round it to 300,000. So you can look it up, I'll put it up over here, or show you it on the wiki page. But about 300,000 kilometers per second. And for those of you that must do miles, it's 186,000 miles per second. That's a lot. So 186,000 miles, well, that's just a little bit short of going to the moon. I mean, the moon's about 210,000 miles away. So the moon light takes just over a second to get to the moon. So if you want to talk to somebody on the moon, you have to wait a second. You can send them the message, they wait a second, they get the message, and then when you want to get a response, let's say you just say, give me a response right now. You've got a computer there, it turns around and gives you a response really quickly, called a transponder. So the computer turns around and gives you a response. You'll get a response in about 2 seconds. Send a response, get it back in 2 seconds. That's the fastest you can get information to and back from the moon. Well, the moon is approximately 1 light second away. That's what we mean. That's as far as light travels in a second, so the moon's about 1 light second away. But that speed is universal, which means that the speed of light is equal to its wavelength times its frequency. Now, typically in an intro level textbook, they won't use the Greek letters, and you might see W times F, where wavelength is W and F is frequency. But it's the same thing. So the frequency times the wavelength is the speed of light, which means that for all light, if the wavelength is long, the frequency is low. And if the wavelength is short, the frequency is high, because the wave travels at the same speed, no matter the frequency, no matter the wavelength. That's not true of all things. Not all things have the same wavelength dependency in the medium. So different things travel at different speeds, and in fact, if you look at the speed of sound in water as opposed to the speed of sound in air, you find something different. The speed of sound, say, in a chalkboard is different than that in air, and the speed of sound in any solid body is much, much shorter than that in air. So these are our basics with respect to wave motion. And, well, there's one other thing I should notice about the nature of wave motion in physical media. Notice when I hit the board, did the board move left and right? No, it didn't shift that way. It flexed up and down as it moved across. There might have been some compression, but effectively the atoms and molecules didn't really move much from their position. The wave itself, the propagation of the wave moved, but the objects inside of there didn't like permanently shift to the right or permanently shift to the left. So it's not the objects moving, it's the shape, is the wave itself. So if this is a water wave again, and we go back and we think, okay, let's look at this as a water wave, not light, but let's just look at it as water. And if we look at a water wave, we say, all right, we got the water, and we got a duck. And a duck we'll have a terrible drawing of a duck. There's his wings, there's his head, there's his little tail, everything like that. He's an ugly duck. I mean, he's a water rat, I don't know what it is. So as it comes along, the wave pushes the duck up and pushes the duck down. So the duck, through time, will go up and down, and up and down, but won't move left and right as the wave pushes it. Now, if the wave has a steep enough gradient, yes, it might push the duck with it. But a gentle, simple waves like these, watch the pond with a duck in it. The duck simply goes up and down and doesn't get pushed by the wave. That's different than a surfer. A surfer then tries to ride and stay in this location of the wave and stay with the wave. But the surfer's falling down at the same rate as the wave goes to the right. So that's how a surfer stays with the wave. The surfer falls down the front at the same rate as the wave goes forward. So you need a fast moving wave that's very steep so you can stay on the wave. So really the surfer's falling down the wave. It's just the wave is moving along at the same rate that he's falling, which is really interesting. So the duck, though, in a very quiet pond, will simply go up and down and up and down as the wave passes under him. So the wave goes across, the duck goes up and down, and the wave motion goes by. So it's actually a disturbance in the medium of the water and not something it pushes. Even with the surfer, the disturbance moves. Most of the water doesn't really move, it just simply moves up and down. So the surfer is actually using the slope of the slope of the wave to actually propel him, rather than the motion of the water. Now, it's not different as the surf breaks. Once it breaks, then there's forward motion, and it curls around. But the water itself doesn't move that much when waves pass through. It just simply cycles around in circles. That's how it works. So, when we think about it, We have these three fundamental things about waves. We have their frequency, which is how many peaks go by you per second. We have the wavelength, which is the distance between the peaks. We have the speed with which they're traveling, which the waves travel by you. And for light, it is a constant thing. It is always the product of the wavelength times the frequency, and that's about 300,000 kilometers per second. That's a constant for a vacuum. And finally, we have the amplitude of the wave, or how high the waves are as they pass by you. Those are the fundamental properties of wave motion. And as we look at light, we'll see how they apply in other ways. Hello, this is Jason Kendall, and welcome to another of my introductory astronomy lectures. Well, last time I discussed the nature of light as being governed by wave principles, and has wavelength and frequencies and speeds and amplitudes, but didn't really get around to how people know this. So let's actually begin. Let's go way back in time, and we'll go back to 300 BC, where the great philosopher Euclid, the Greek philosopher Euclid, actually in all of his work also discussed the nature of reflection. So he saw that actually the light was reflected off of surfaces. And so when we look at the nature of reflection, Euclid posited that as light hits a surface, the angle of reflection equals the angle of incidence. So this is kind of like when you actually throw a ball against a wall at an angle, it actually reflects off the same wall. And so Euclid started to thinking, well, maybe light acts like a particle. And because it goes in these because it bounces off of surfaces like a particle does. Well, that was 300 BC. And then we come along 400 years later, and Ptolemy, remember him? Claudius Ptolemaeus made the Almagest, did all the geocentric stuff. He also did important things with respect to light. And in about 140 AD, he discovered a relationship for refraction. So he discovered that the angle of incidence is proportional to the angle of reflection, the angle of incidence from one medium, say air, through a surface like water. Then if you the light is refracted. So the angle of incidence is proportional to the angle of refraction after it passes through the new medium. And that's why when you take a stick and put it into water, the stick looks like it's bent. That's because the light that's coming out of the water, that's reflected off of the stick that's in the water, comes out of the water, the direction of the light is changed because the angle of incidence is different than the angle of refraction as it goes from one medium to another. However, Ptolemy couldn't compute anything other than they were proportional to each other. Then about 800 years later, the Iraqi philosopher named Ibn Sal in about 980 AD, maybe 984 AD, actually determined that the angle of incidence, the sine of the angle of incidence, divided by the sine of the angle of refraction is equal to the speed of the wave, the speed of light in one medium to the other medium, and then to the reciprocal of the index of refraction of the refracted medium to the inbound medium. So that's what he learned. And he learned that's what was the proportionality. It had to be proportional to the speeds of the light coming in. Well, he couldn't, because it's 984 AD, Ibn Sal from Iraq didn't have any way of measuring the speeds of light. He knew the ratio and the proportionality of the speed of light is different from one medium to another. The speed of light in air is different than the speed of light in water. And that's why there is refraction. So refraction is a manifestation of the differing speeds of light in the two media. All right, well, that's 984 AD, and people are starting to figure out things about light. And in 1020 AD, about 40 years later, another Iraqi researcher, natural philosopher, by the name of Ibn al-Haytham, was discovered and correctly posited that light is not emitted by the eye, it is rather received into the eye. Now, that's a very interesting way of thinking because it changes the nature of philosophy. Because when people think about seeing things, they think about, oh, I'm looking at this thing. So therefore, when I look at it, it becomes visible. That's a fascinating way of thinking. So where does light come from? Well, we can think of light philosophically, we can think of light emanating from you and going out to that thing, illuminating it such that we can see it. That's a philosophical concept, but it's not borne out by reality. So illumination, or being able to see something, is not reflective of reality. But you can see why people would say that, because a blind person can't see. Why? Because their eyes don't emit anything. We still have such ideas inside of our current, how should we say, mythology. Superman has eyes that beam out laser beams or heat vision. You have, from the Marvel side, of course, you have Cyclops, who, when he takes off the guard, he's always got spraying his vision, his laser vision out his eyes. So the concept that the eye, what you see, you impact, is a very ancient idea, and it's part of mythology and culture. But it's not how it works. And this is how Ibn al-Thayyib determined how it worked. He looked at the nature of a camera obscura. So he's in the Iraqi desert, and it can get the sunlight can be extraordinarily intense, and the sand around can be extremely intense. So what he did is he used a camera obscura. So what he would do is he'd go inside a darkened tent, a very, very dark tent with no sunlight coming in, dark as possible. And then he would let it make a little tiny hole on one side of the tent such that light could come in only in that beam. And then what he noticed is that if the rest of the tent was extremely dark, the hole acted as a camera obscura, which meant that the light was reflected off of, say, like maybe a palm tree or something like that, or another building or another tent, dare I say a camel. But the light would reflect off that thing, go through the hole in the camera, and then be inverted as it passes through and makes an image on the far side of the tent. So when he thought about this, he said, well, wait a second. The eye is like a little tent. And the iris of the eye, which is where the pupil of the eye, is where the light comes into. It gets inverted, and the eye then acts like the tent, and the pupil of your eye acts like the lens. So the camera obscura is the tent with one little hole in it, is exactly analogous to what the eye does. So the image that's formed on the far side of the tent is exactly how the eye works. The light is reflected off the object, comes through the pupil of the eye, the diameter is modulated by the pupil, and then it makes an image on the back of the retina. And that's how your eye works. And so it's a camera obscura, actually with a lens, so that it actually is more focused. So so he discovered this in about 1020 AD, and finally got to the point where it's like, wait a second, it's not that the eye emits light, it's that the light comes through and then makes a picture that then we see. So reflection off of objects and then reception by the eye is how it works. So that's an amazing discovery, considering the weight of philosophical ideas against it and the way people think about it. In fact, you ask people how you see things, they might even think that they reach out with their eyes. And in fact, a lot of mystics think this too. It's easy to find people who would think this, and in fact would justify it on mystical grounds. So in any event, that was actually shown in the deserts of Iraq. During the European Dark Ages, science was flourishing across Islam, and specifically in Baghdad in Iraq, then Baghdad and now current day Iraq. So then it comes along again, the Dark Ages are starting to fall in Europe, and in 1307, well, they're not so dumb. The Dark Age during the Dark Ages just means it's not the Renaissance, but medieval thinkers are still on target with things. In 1307, a German natural philosopher, Theodoric of Freiburg, comes up with an idea. What he does is he wants to understand rainbows. So what he does is he takes glasses filled with water and lets beams of light from the sun reflect around inside droplets of water. And he demonstrates that he can create rainbows by having the beam of light go at various angles of incidence inside of drops of water. So he determines then that rainbows in the sky are made by refracted light through water in the sky. And he in fact determines the angle that it takes in order to refract the light around inside a raindrop. And he notices that the angles of refraction and bouncing around inside the raindrop correspond exactly to what the angular separation of the sun is from the rainbow in the sky. So he determined that, well, by measuring the nature of the rainbow in the sky and its angle away from the sun, and what it takes in order to reflect light around inside of drops of water, the angles that it takes, that tells you exactly how rainbows are formed. It's refracted light through water. Well, then that partly goes towards the wave nature of light, along with the refraction is a wave phenomena, and then even the camera obscura is kind of a particle-like phenomena because it shows rays, and then we have reflection, which is kind of like a particle-like phenomena. So, because those are like bouncing things off of things. But then there was a real clincher. In 1660, Italian Franco Grimaldi actually determined that light spreads out. So, meaning most people thought, because of these particle concepts of the camera obscura and reflection, that light behaves very much like a particle. But if people are saying that, they say, well, wait a second, if it behaves like a particle, there's no way that the particles will spread out like water waves. So if you have a barrier with a small hole in it and water comes up against that barrier, when the waves hit from the water outside the barrier, like a dike in a river outside of a harbor, the waves will spread out from that point, and as though that's the point of origin. So they'll spread out in a semicircular pattern. That's water waves. What Grimaldi did is he showed that also happened with light waves. So he determined that light doesn't just act like a particle, but it acts wave properties. And so by making a slit through which water passed in 1660, which eventually was published in 1665, the wave nature of light due to diffraction, which it diffracts around a boundary. So as light comes through a hole, it diffracts around that boundary and spreads out. That product of diffraction only happens as a wave. And so this started to solidify the concept of a wave nature of light. And then along comes Isaac Newton, who then really starts to try to understand the way rainbows are formed and how that all works. So let's look at what Newton's contribution is next time. Hello, this is Jason Kendall, and welcome to another one of my introductory astronomy lectures. Well, last time we talked about the nature of how light works, and we went back and further and talked about the nature of how the wave model of light was probably the predominant idea. And then we threatened to bring on Sir Isaac Newton. Well, let's see what he had to say. All right, in 1666, that's almost 110 years before the birth of the United States, 1666, he wasn't Sir Isaac Newton yet, Isaac Newton bought his first prism. And what he did is he was trying to determine what the nature of light was. He was extraordinarily curious about light. And so he bought his first prism and learned to grind lenses himself. But what he did is he wanted to disprove the wave theories of light. He firmly thought that the nature of light was that it was particles. And he called these particles corpuscles. It's a wonderful word, but the idea is that the light is constructed not of waves, but of corpuscles, of things going through. Why did he think that? Because with his experiments of light, he thought, well, let's see. Now, if you're going to bounce something off of a surface, if a thing bounces, like a ball bounces off of a surface, the angle of the incidence of the ball at the surface equals the angular reflection, if the surface is perfectly smooth. So let's say we look at a mirror. You can take a beam of light from the sun, make a tiny hole in, say, a curtain that goes outside, and the beam of light goes through, maybe there's some dust so you can see the beam, and then it hits the mirror. The mirror is a flat surface, and then it reflects off in a new direction. But the angle of incidence, meaning make the mirrors flat, think about a stick going straight down the middle to the mirror, as the angle that hits here is exactly the angle that leaves there with respect to the vertical angle. So just think of it as a plumb bob down to a flat surface of the mirror. And so the angles are always the same. Now what Newton posed is that this is what light does. Since light does that, and that's what particles do, so therefore light must be a particle. Otherwise it wouldn't have this property of reflection. So it also has the possibility of actually going in a ray. Since it actually goes in a ray, and we know that waves spread out on water, say a waves just don't stay in a line, they actually spread out. So Newton said, well, it can't be a wave because I can make rays of light through curtains and make beams. I can do that. And it reflects like particles. So therefore it must be. Now, he did have to come up against the significant evidence that it has wave properties such as diffraction. But in any event, so he bought his prisms and started playing around with them in 1666, and it took a long time, almost a decade, for him to actually come up with those ideas about it. In 1672, he was in the Royal Society, and he published his ideas, or at least promulgated his ideas about the corpuscular nature of light. And what he said is, he argued to the society this time after doing numerous experiments to try to determine this. He also argued for the existence of 7 different colors of the spectrum. In fact, that's where we get our Roy G. Biv from: red, orange, yellow, green, blue, indigo, and violet. He established 7 colors, even though there's a spectrum, even though there's not just 7 colors. But Newton was a mystic, and 7 was a mystical number, so linking light with mysticism was very Newtonian at the time. And so when Newton presented his ideas, he was attacked, well, by his old rival, Robert Hooke. So what did Newton present? Well, Newton said that because the prevailing idea of the wave theory of light could not readily explain the action of prisms or the actions of rays, everyone thought that prisms, or when you pass light through a material like glass, the glass corrupts the light, adds color to the light. And when it adds color to the light, it changes the light. So Newton said, but wait a second. So he took one prism, shone a beam of white light, sunlight, through it, and it spread it out into a rainbow. Then what he did is he took a second prism and put it into to intercept the rainbow of the first prism. And if you angle it just right, what happens? Well, out comes white light. So the first prism breaks the light into a spectrum. The spectrum then travels a little bit till it meets the second prism. The second prism then recomposes the light back into white light. And so you get a beam of white light in, then a spectrum in the middle, and then a beam of white light coming out. And so Newton said, well, wait a second. Light can't be corrupted by the glass because out it comes. If it was corrupted, then it should spread even further. And also what Newton did is he took the 2 prisms and he actually offset one so that just the red part of the spectrum intercepted the glass of the second prism. And what passed through the second prism? Just red light. The red light was neither added to or destroyed. It simply was redirected by the second prism in a new direction. That's all it did. So Newton said, well, if it's corrupting, then the red light should have turned into blue or purple or green or what have you, but it didn't. It stayed red. So another argument for it is that Newton said, I know that the glass isn't corrupting it because, well, I can polish glass. And that's a very interesting statement. Because you can polish glass, you know it's not corrupted. All right, so what does he mean? When you take a piece of glass that's roughly made, there might be air bubbles in it, there might be sides on it. So what do? You take that and you grind it with sand or sandpaper or some sort of rough surface. And the rough surface then gets rid of all the big edges. And they use finer and finer and finer sanding agents in order to get at smaller and smaller and smaller imperfections on the surface of the glass. So what happens is eventually you have a perfectly smooth glass, there are no imperfections, and the light becomes more and more and more clear. So the spectrum of light becomes more clear as you polish it, which means that you're getting rid of corruption in order to get what the people thought was corruption. So Newton thought the whole idea of the corruption of glass to be wrong, and that and in fact he is correct. He was correct about that. But when he presented all his ideas to the Royal Society in 1672, it was a huge debate, a huge hullabaloo, and Robert Hooke really attacked him for it because Robert Hooke really they just had a terrible rivalry. And Robert Hooke advocated the wave theory of light based on refraction and diffraction, it wasn't a settled matter. And as a result of the public nature of this battle, Newton stopped talking about it, stopped engaging in the debate about light for a very long time. Well, about 6 years later, Christian Huygens set out to disprove Newton's idea about the corpuscular theory of light. And he did so by trying to incorporate the nature of refraction and reflection into a wave theory of light. And that was very difficult for him, but he managed to do it in some ways. So he advocated the wave theory, and light was acting as a wave, but he ran up against some problems. And one of the problems was, it had been known for a long time, since about the time that Newton got his first prism, that there are certain kinds of rocks, calcite crystals specifically, that were clear. They were crystal clear. However, when you looked at them, they made multiple images. So the crystal itself, it seemed to be clear. When you passed something through it, passed light through it, or you just looked at an image through it, there'd be multiple images that would occur. Nobody could really understand what this was going on, but so these calcite crystals would make them. And even weirder is that if you took one calcite crystal and put it on top of another calcite crystal and looked through that, there'd be nothing. It'd block the light. So they didn't really understand what that was at all. And Huygens' idea about how how waves propagate through materials was not well understood. And so basically, Huygens originally thought, well, they've got to be different kinds of light. Maybe some are circular, spherical waves, and some are ellipsoidal waves, and you add them together, that might make the calcite. But that really didn't help at all. The ideas about why these crystals worked this way was not well understood, even though their phenomenology was well established. All right, so 1703, wow, a whole long time after that, Hooke dies. And when Robert Hooke dies, Newton is actually a little bit glad. 1704, he publishes his Optics, which is his great volume of work about how to do all of the experiments that he described back in 1672. He described exactly how to do them so people could more easily replicate them and prove the corpuscular theory of light. Well, Newton truly advocated this corpuscular theory, and because of his success with the laws of motion, because of his success with Principia, because of the success with gravity, his ideas carried enormous weight. And so people thought that the optics was the correct way, and that the corpuscular theory held the day for a very, very long time. So how did Newton approach the idea about the crystals? Well, he said, well, light, maybe since they're corpuscles, they might have sides. They might have a left side, a back side, a front side, and these sides might be different. And so the different sides then allow you to bounce differently inside a crystal. So it was his argument. And, well, that's how he explained it. It wasn't a very good argument, but it's fascinating he thought about the concept of sides. All right. So when we look at the nature of what he was talking about in 16, we find that his Optics was an extremely large influence on scientific thought, and even well after he died. He died in 1727, and his work continued on. We still use his laws of motion. We talked about them before. We still use his law of gravitation. We talked about that before as well. But we don't use his corpuscular theory of light anymore. So there was many more advances to occur in order for us to understand what this nature of light is. And part of the reason I'm kind of going through this historical aspect of things is because sometimes when we look at an introductory level textbook or something, it'll just tell you what was done. It doesn't describe the battles that people had. There were interpersonal battles between Newton and Hooke, and the ideas relied on experiments which couldn't necessarily be done by them very easily at the time. And these were new ideas. In fact, when Newton started working with prisms, they were new toys, and so people didn't think they were really valid scientific instruments for a long time, or couldn't even make them so you could regulate them because there was no theory about why they worked, so how can you use them scientifically? So as knowledge dawns, as knowledge grows, it's important to know where it comes from, because it comes out of human interactions. It comes out of people working together or against each other to try to get ideas out there. And one person says, well, I don't think that's right. And where Christian Huygens thought that Newton was wrong, he wasn't really mean about it. He just didn't agree. So Hooke was really mean about it, though, and he attacked Newton. So all these interesting interpersonal relations that occurred through the history of science. And that's what we should expect, actually, when we look at anything done by people. So next time, we'll see how Newton's corpuscular theory finally was dethroned. Hello, this is Jason Kendall, and welcome to another one of my introductory astronomy lectures. Last time we talked about the nature of how Newton contributed the particle theory of light, which he called the corpuscular theory of light, where he said that every particle of light has its own color, and so the combination of the corpuscles makes white light, and a prism acts to separate out the various corpuscles into their various constituent colored bodies. And so this was a very compelling idea, and with the publication of Newton's optics in the latter part in 1704, it became the standard idea for how light works. But it wasn't totally settled, because Newton's ideas about light didn't perfectly explain a lot of phenomena. So what happens next? Well, Newton's theory about how light works. And remember, a theory in this sense is the best explanation for the experimental facts of the day. And so as experimental facts change, then theories must also change. And that's exactly what happened. Because in the early part of the 19th century, all the way through the 19th century and into the 20th century, the nature of how we can actually make measurements radically changed, which radically changed our understanding of how things worked, and that meant we needed new theories. So it's not that people are dumb and they were wrong, it's that new things come to light that need to be explained. So let's see what happened. All right. So Newton's idea carried the day for almost a century. And in 1803, Thomas Young came up with an amazing idea that actually had influence all the way through for 100 years and into the 20th century that actually influenced quantum mechanics. But let's see what that is. What he did is he said, well, I really want to test this idea of corpuscular theory. He doubted it. And so he said, well, how can I do this? What he found is that he could make a steady beam of light and have that go to a barrier. And that barrier can have two vertical slits in it. Now, by 1803, he was able to make very narrow slits. The technology had advanced such that we could make slits, such that people could make slits not just a millimeter wide, but 1,000 times smaller than a millimeter, a micron. Very tiny slits. And so these tiny slits where light was allowed to go through. So let's say you take two of these slits and put them very close together, say a centimeter or so. And when you have light approach these two slits, all the light gets blocked except for these two vertical slits. And on the other side of the barrier, then the two slits act like point sources or vertical line sources. But if you make a measurement on the far side, the wave properties of these slits become evident. Now, if it was Newton's corpuscular theory, and you shoot a whole bunch of bullets, say now corpuscles are like bullets, and so the light source is like shooting bullets at something, the light goes to the two slits, and if it happens to, you can then draw a line from the source to the slit, to the wall behind the slit, and that would be a straight line. And so rays and bodies like corpuscles must necessarily follow straight lines. And so if the corpuscular theory of light was correct, then this experiment should show two spots on the far side at the same width as the two slits are and roughly the same diameter of the slits. Maybe there's a little bit of spread due to randomness, but we should expect only two slits. Something different was discovered. What Thomas Young discovered was that there was an alternating band of light and dark and light and dark and light and dark and light and dark and light and dark all the way out. Many alternating lights and darks. And if he moved the barrier, at least where you detected it, closer or farther away, the position of the light and dark locations changed. So what this meant was that light was acting like waves in water. And so if you would then take a barrier like a jetty or a dike where water is coming up through, then as the water goes through the opening, it spreads out, and water can either water waves either constructively interfere or destructively interfere. And so what Young proposed was that just like water waves, light waves follow what we call the superposition principle, meaning if you have two waves and they collide against each other, so one's going like this and one's going like that, and they're moving towards each other, by the time they meet, if one's at the top at the point of meeting and one's at the bottom, the crest is at the here and the trough is here, then the wave cancels each other out and there's no motion. But if the waves are, when they meet, they're both at a crest or both at a trough, then it doubles the height, depending. So if they're like this when they meet, then actually it's much deeper. Or if they're like this when they meet, so they come together and they meet, they rise much higher. So they add together. So the amplitudes of the waves meet or add together. The amplitudes of the waves add together when the waves meet at a point, and that's the superposition principle. And sometimes that means that there appears to be no waves at all, and sometimes that means that there's a lot of waves, or the waves are much, much larger. So the two sources of waves, when they meet, that adds them together. Their amplitudes add together linearly, which means they don't multiply together, they don't exponentiate together, they simply add together. And that adding of waves is what, as combined with the fact that they're spreading out, is what Young saw on the far side with his detector on the other side of the barrier with the two slits in it. And that was the beginning of the confirmation of the wave theory of light. All right, so we're not quite done with Newton's idea yet, because Newton had some kind of other explanations for light. But let's keep going with this and see how long he can hang on. In 1816, just about 12 years later, Fresnel determined that light was essentially a transverse wave, and so did Thomas Young in 1817. And in 1817, Fresnel worked out the mathematics for diffraction. And so these enormous equations that he worked out, he presented them as a result of the Royal Society saying, we want to solve this problem of diffraction once and all, da 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 da. And so Fresnel worked out the math. It was extraordinarily complicated, but in order to do it, he had to use the wave theories of light, not Newton's corpuscular theories. And everybody judging this competition for figuring out the solution to the diffraction problem, they were all Newtonian advocates. They advocated the corpuscular theory. So they had some problems with it. They first dismissed it. But one of the key predictions that Fresnel had is that if you put a barrier in between a source of light and the place you're detecting, and you actually do what Young did, but you have just a small opening and then put a barrier there, it is possible for there to be a bright spot directly behind the barrier, which is really kind of weird. And so that's as a result of diffraction. Now the barrier can't necessarily be huge, like 20 yards across or something. I know that's called a shadow. But if the barrier is small, then you should be able to see a bright spot directly behind the barrier. If the slit is narrow and the barrier and then the block right on the other side of the slit is kind of small but not too big, then you should be able to adjust the situation so you have a bright spot there with the barrier in bright spot on the far side of the barrier. On the other side of the block. So you have a barrier with a slit, a block, and then where you're detecting it. And if you do it just right, set things up just right, then you should be able to make a bright spot on the far side of the block. And that was a prediction of Fresnel. And everybody was like, this is crazy, that can't happen. But because it's an experiment and because it was predicted, it was done. And so in 1819, this idea was confirmed. And therefore, it solidified, combined with the double-slit experiment and Fresnel's solution of diffraction ideas, the solution of the diffraction problem, Newton's corpuscular theory of light was completely destroyed. Well, to some extent. We'll find that in a different form, it rises back up in the 20th century due to a guy named Albert Einstein. But in any event, the corpuscular theory, as Newton described it, no longer explained sufficiently everything that was out there. So that put the nail in the coffin for Newton's theory of light. That was 1819, a good 100 years after Newton did his work. All right, so in 1821, Fresnel and Young advanced even further. They proved that all light was a transverse wave and had no longitudinal component. Before then, people thought that there was how did waves work? If we do sound waves, remember sound waves are compression waves where things compress, and you can have transverse waves like water waves going up and down. You can even have side-to-side transverse waves. So there's two kinds of transverse waves. Well, actually, we can think of there being two kinds of waves. Waves of pressure going in and out as the wave progresses in a direction, or we can think that waves wave up and down perpendicular to the orientation, to the direction in which they're traveling, like water waves. Water waves, though, don't go left and right as they traverse across the ocean. They only go up and down. Now, they might go side to side as they collide, and the sea foam sprays everywhere. But waves go up and down as they go, and that's called transverse. Transverse to the propagation of motion. Well, what is found is that light can be transverse in any direction to its motion. To its direction of motion. So if light can be a transverse wave, up and down, side to side, back and forth, so it can go like this, or like that, or like this, as it's going towards you. So those are transverse components, or perpendicular to the direction of motion. So why did they think this? And that's because in 1821, Fresnel showed that this would explain the behavior of calcite crystals. Remember them from last time? Calcite crystals form double images, and if you take one calcite crystal and rotate it with respect to the other, the image of the thing on the far side disappears. Well, that's the reason, is because the structure of the crystals acts like little picket fences. And what's a picket fence? Okay, so a picket fence is just a series of slats, a series of Young's double slits, slits. And so light can only pass through the slit if its transverse wave is going in the same direction as the slit. So that's really interesting. We call this polarization. And polarization is the idea that the light has an has a distinct orientation for its transverse component. Like I said, it can go any direction, right? But if we then put a barrier, like Thomas Young's double slit experiment, or just even a single slit, then light only, if this long slit like this, then the light can only go through if it has the same orientation of its transverse wave as the size of the slit. Now, if the slit's really big compared to the amplitude or wavelength of light, then it can make it through in any direction. But if it's longer, then the slit will determine which way it can go through. Just in the same way that a frisbee thrown at a picket fence, the frisbee, if it's going end over end, can slide between the slats of the picket fence. But if it's going flat, like a frisbee normally does, it gets blocked by the picket fence. So when you're playing frisbee and you want to make a scoring box, maybe you want to throw it into a box, you take the picket fence idea and you turn it on its side. Then you have slats going like this. Then the frisbee can go in between the slats. If the picket fence is going up and down, meaning the slats are like this, like a ladder, then the frisbee can go in between the slats. But if the picket fence is like on the side of a road in front of a house, then as you throw the frisbee at the picket fence, it can't go between the slats because it's long and the slats are narrow. So the frisbee is polarized flat to the ground, and the picket fence around somebody's house is the slats are polarized up and down, perpendicular to the ground. So a frisbee can't go in unless you finesse it or English it, and it goes in the right perfect way, and then everybody thinks you're really cool for being able to do that. But in any event, polarization was described as the idea that since light has a transverse component of waves, not a longitudinal wave, meaning it doesn't pulse back and forth as it comes towards you or away from you, or in the direction of motion that it goes, it doesn't go like this. Along the direction of motion, doesn't compress as long as it goes. It only has a transverse component. Then we can use the fact of the transverse component of the wave to explain polarization. And polarization is then how we have this picture of light. As it travels, it has these longitudinal components, meaning up and down or side to side components to the light wave. And that's where that picture comes from, is the necessity of explaining polarization. Well, that's a big step into the understanding of the nature of light, and next time we'll talk about the even more contributions from 19th century science as people discover more and more aspects. And we're going to see how Michael Faraday and others contributed to that knowledge next time.